Mars, Whispers from the Red Planet. Welcome back to our cosmic campfire, dear dreamers and stargazers. Tonight we're embarking on a journey that spans millennia, crossing the vast darkness between worlds to visit our mysterious neighbor, Mars, the Red Planet. Pour yourself a warm cup of tea, dim the lights, and settle into your most comfortable spot. This is a story that unfolds like the universe itself, slowly, mysteriously, and with infinite wonder. We'll travel through time together, from ancient civilizations gazing up at a wandering red star to the moment humanity first touched Martian soil with robotic hands. This isn't just a story about a planet. It's a story about us, about our eternal need to explore, to wonder, and to reach beyond the boundaries of our world. So close your eyes when you need to, let your imagination soar, and join me as we whisper back to Mars, the planet that has been whispering to us for thousands of years. Let our journey begin. The ancient ember in the sky. Picture, if you will, a warm evening 5,000 years ago. The sun has just surrendered to the horizon, painting the sky in watercolor washes of amber and rose. In the fertile valley between two great rivers, the Tigris and Euphrates, a Babylonian astronomer climbs the steps of a ziggurat, his sandaled feet creating soft echoes against the ancient stone. His name is lost to time, but his wonder remains eternal. As he reaches the summit of this earthly tower, he carries with him a clay tablet and a reed stylus, tools as precious to him as a telescope would be to astronomers thousands of years in the future. The first stars are beginning to pierce the deepening blue, tiny pinpricks of light in heaven's vast tapestry. But tonight, like many nights before, his attention is drawn to something different, something that doesn't behave like the other stars. While his celestial companions hold their positions in their eternal dance, this one wanders. This one moves with purpose across the dome of night, glowing with an ember-red light that seems to pulse with mysterious energy. The Babylonians called it Nergal, after their god of war and destruction. They watched it trace its strange path across the sky, sometimes racing forward, sometimes slowing to a crawl, occasionally even appearing to move backward in a cosmic ballet that defied understanding. Little did they know they were witnessing the orbital mechanics of two worlds, their own Earth and the planet we now call Mars, as they pursued their endless journey around the sun. But Mars was calling to more than just the Babylonians. Across the ancient world, civilizations looked up and saw this wandering red star, each interpreting its message through the lens of their own culture, their own hopes and fears. In ancient Egypt, along the life-giving Nile, astronomers called it Hor Desher, the Red One. They associated it with the god Horus, the falcon-headed deity who ruled the sky. Egyptian priests, with their deep understanding of mathematics and astronomy, carefully tracked Mars's movements, incorporating its cycles into their complex calendar systems. They saw in its red glow the promise of flooding seasons and harvest times, the eternal rhythm of life and death that governed their civilization. Far to the east, in ancient China, astronomers gave Mars the poetic name Yinghuo, the fire star. Chinese scholars, with their meticulous record-keeping that would put many modern institutions to shame, documented Mars's movements for centuries. They believed it represented the element of fire and associated it with the emperor's mandate from heaven. When Mars appeared bright and prominent, it might signal changes in leadership or great events to come. The ancient Chinese understood something profound about Mars that would take Western astronomy centuries to rediscover. That its behavior was predictable, cyclical, part of a grand cosmic clockwork. But in ancient India, Sanskrit astronomers called it Mangala or Angaraka, names that evoked both the planet's red color and its association with fire and energy. Imagine the Greek philosopher Apollonius of Perga, around 200 BCE, walking the marble halls of the great library of Alexandria. The Mediterranean breeze carries the salt scent of the sea through the open windows as he contemplates a problem that has puzzled astronomers for generations. How could the gods create a wandering star that sometimes moved forward and sometimes moved backward? Apollonius proposed an elegant solution that would influence astronomy for over 1,000 years, the theory of epicycles. He suggested that Mars moved in a small circle, called an epicycle, while that circle itself moved along a larger circle around Earth. When Mars was on the part of the epicycle moving in the same direction as the larger circle, it appeared to move forward. When it was on the opposite side, it appeared to move backward. It was beautifully complex, mathematically sophisticated, and completely wrong, but it was wrong in a way that showed the profound human drive to understand, to create order from chaos, to find patterns in the seemingly random dance of celestial bodies. Picture those ancient observers on their rooftops and temple towers, night after night, year after year, watching Mars trace its mysterious path. They couldn't know they were looking at a world, a planet much like their own, with seasons and weather, with polar ice caps and dust storms that could engulf the entire globe. They couldn't imagine that Mars had once been warmer and wetter, that ancient rivers had carved channels across its surface, that it might once have harbored life. All they knew was wonder. All they had was the patient discipline of observation and the burning human need to understand. In their careful notes and calculations, in their myths and stories, they were laying the foundation for everything that would come after. Every Mars mission, every rover that has ever rolled across Martian soil, every image we've received from that distant world, it all began with those ancient astronomers looking up at a red point of light and asking the most human of questions. What is that? And why does it move that way? The whispers from Mars had begun, carried across the void on beams of red light, and humanity was listening. The Renaissance awakening. Fast forward through the centuries, past the rise and fall of empires, past the quiet preservation of knowledge in monastery libraries during Europe's Dark Ages, past the brilliant flowering of Islamic astronomy that kept the flame of scientific inquiry burning bright. We find ourselves in 16th century Europe, where the very foundations of human understanding are about to shift like tectonic plates beneath our feet. The year is 1543, and in a small town in what is now Poland, an aging canon named Nicholas Copernicus is putting the final touches on a manuscript that will change everything. But Copernicus is hesitant, almost afraid to publish his work. He knows that what he's proposing will shake the very pillars of accepted truth. Picture him in his study, surrounded by books and astronomical instruments, the soft glow of candlelight flickering across pages covered with mathematical calculations and celestial diagrams. Outside his window, the same Mars that captivated ancient astronomers continues its wandering path across the night sky. But Copernicus is seeing it with new eyes. What if Earth isn't the center of everything? What if the sun holds that honored position instead? What if Earth, along with Mars and the other planets, orbits around our blazing star in a grand cosmic dance? The implications are staggering. If Earth orbits the Sun, then Mars's strange retrograde motion suddenly makes perfect sense. When Earth, moving faster in its inner orbit, overtakes Mars, it would appear that Mars is moving backward, like a slower car on a highway that seems to move backward when a faster car passes it. Copernicus's revolutionary idea, published in his book De Revolutibus Orbis Celestium just before his death, placed Mars in its proper context for the first time in human history. Mars wasn't just a wandering star guided by the whims of gods. It was a world, orbiting the sun just as Earth does, following predictable laws of motion. But ideas, like rivers, need time to carve their channels through the landscape of human thought. It would take the genius of Johannes Kepler, working decades later, to fully unlock the secrets of Mars's motion. Imagine Kepler in Prague in the early 1600s, hunched over his desk in a room lit by the pale light of dawn. He's been working through the night again, surrounded by the meticulous observations of Mars made by his mentor, the great Danish astronomer Tycho Brahe. Tycho had spent decades tracking Mars's position with unprecedented precision, using instruments of his own design in his magnificent observatory on the island of Hen. Now Kepler, armed with Tycho's treasure trove of data, is trying to solve the puzzle of Mars's orbit. He's been working on this problem for years, filling hundreds of pages with calculations, trying to make Mars's observed positions match the circular orbits that everyone assumed the planets must follow. But Mars refuses to cooperate. No matter how Kepler adjusts his circular model, no matter how many epicycles he adds, Mars stubbornly refuses to be where the mathematics says it should be. The difference is small, just 8 minutes of arc, about the quarter of a full moon. But Kepler is a perfectionist. 8 minutes of arc might as well be 8,000 miles.
Then, in a moment of inspired desperation, Kepler makes a leap that will echo through the centuries. What if planetary orbits aren't perfect circles at all? What if they're ellipses, flattened circles with the sun at one focus? It's a radical idea. Circles had been considered perfect since ancient times, the ideal shape for celestial motion. But when Kepler applies his elliptical orbit to Mars, something magical happens. The planet's observed positions match his calculations perfectly. Every single one of Tycho's precise measurements falls exactly where Kepler's elliptical orbit predicts it should be. In that moment, in that drafty room in Prague, Mars reveals one of the fundamental secrets of the cosmos. Planets don't move in perfect circles. They follow elliptical paths, sweeping out equal areas in equal times as they orbit the sun. Kepler has discovered his first 2 laws of planetary motion, and Mars has been his teacher. Picture Kepler the night he makes this breakthrough, stepping outside into the cool Prague air, looking up at the red planet that has been his obsession for so long. Mars appears as just a tiny dot of light, no different than it had appeared to ancient Babylonian astronomers. But now Kepler knows something those ancient stargazers couldn't have dreamed. He knows Mars's true path through space, understands the elegant mathematical poetry of its orbital dance. In his journal, Kepler writes with the passion of a man who has glimpsed the mind of God. "I have stolen the golden vessels of the Egyptians to make a sacred vessel for my God." Mars has shown him that the universe operates according to mathematical laws, that chaos is really hidden order waiting to be discovered. But even as Kepler celebrates his triumph, he knows this is just the beginning. Mars has whispered one of its secrets, but the planet itself, the physical world that produces that wandering red dot, remains as mysterious as ever. What is Mars made of? Does it have mountains, valleys, weather? Could anything live there? These questions would have to wait for a new kind of explorer, not the human eye aided by careful observation, but the telescope, that revolutionary instrument that would soon open new windows onto distant worlds. Through the Looking Glass. The year is 1609, and in the bustling city of Venice, a middle-aged mathematics professor named Galileo Galilei has just heard rumors of a remarkable new invention from the Netherlands, a device that can make distant objects appear near. Intrigued, Galileo immediately sets about constructing his own version of this spyglass, improving on the design until he has created something unprecedented, a telescope capable of magnifying objects 20 times. Picture Galileo on that first night he turns his homemade telescope toward the heavens. The date is January 7th, 1610, and he's pointing his instrument at Jupiter, already excited by his discovery of mountains on the moon. But tonight, something else catches his attention through the eyepiece. 4 tiny points of light arranged in a line near the bright planet. By the next night, they've moved. By the third night, one has disappeared behind Jupiter itself. Galileo has discovered Jupiter's 4 largest moons, proving that not everything in the universe orbits around Earth. But more importantly for our story, he has demonstrated the power of the telescope to reveal hidden worlds. Soon, astronomers across Europe are turning their telescopes toward Mars, hoping to unlock its secrets. But Mars proves to be a difficult target. Unlike Jupiter, which is large and bright and always shows a disk through a telescope, Mars appears as nothing more than a tiny reddish dot most of the time. Only when Mars comes close to Earth in its orbit, an event called opposition that occurs roughly every 2 years, does it grow large enough to show any detail. The first astronomer to report seeing actual features on Mars was a Dutch scientist named Christian Huygens. Picture him in 1659 in his observatory in the Netherlands, peering through his telescope during a favorable opposition of Mars. The planet appears as a small, blurry disk, but Huygens can make out a dark, triangular marking on its surface, a feature we now call Syrtis Major. More importantly, Huygens notices that this marking moves across the face of Mars, disappearing around one edge and reappearing on the other. Mars, he realizes, is rotating on its axis just like Earth. By timing how long it takes for the marking to return to the same position, he calculates that a Martian day is about 24 hours long, remarkably similar to our own. As telescopes improve over the decades, Mars begins to reveal more of its secrets. Giovanni Cassini, a brilliant Italian astronomer working at the Paris Observatory, observes the white polar caps at Mars's north and south poles. Like patches of snow on a distant mountain, these caps grow and shrink with the Martian seasons, suggesting that Mars, like Earth, is tilted on its axis and experiences seasonal changes. William Herschel, the German-born astronomer who discovered Uranus from his garden in England, makes even more detailed observations. Using his superior telescopes, Herschel can see seasonal changes in Mars's surface features. Dark areas become more prominent during the Martian spring and summer, then fade during autumn and winter. Could these be vegetation, responding to seasonal changes just like forests and grasslands on Earth?
Imagine those 18th and 19th century astronomers spending long, cold nights at their telescopes, sketching what they could see of Mars' surface. Each favorable opposition brought new opportunities to study the red planet, and each observation added another piece to the growing puzzle. They saw what appeared to be continents and oceans, dark regions they named seas and lakes, lighter areas they called lands and continents. They gave these features poetic names that still grace Mars maps today: Mare Erythraeum, the Red Sea; Sinus Meridiani, the Meridian Bay; Terra Arabia, the land of Arabia; Mare Cimmerium, the Cimmerian Sea. But the most dramatic observations were yet to come. In 1877, during a particularly favorable opposition when Mars came closer to Earth than it had in decades, an Italian astronomer named Giovanni Schiaparelli made observations that would capture the world's imagination and fuel decades of speculation about life on Mars. Picture Schiaparelli at his telescope in Milan, carefully mapping the surface features of Mars with unprecedented detail. As he traces the boundaries between light and dark regions, he notices something remarkable: thin, dark lines stretching across the planet's surface, connecting the various seas and continents like a vast network. Schiaparelli calls these lines canali, an Italian word meaning channels. He imagines them as natural waterways, perhaps connecting the polar caps to the darker regions he believes to be seas.
But when his observations are translated into English, canali becomes canals, a word that carries very different implications. Canals, after all, are artificial. Canals are built by intelligent beings for a purpose. And suddenly, the idea that Mars might not only harbor life, but intelligent technological life, captures the public imagination like wildfire. The whispers from Mars have grown louder, more insistent. No longer is the red planet just a wandering star or a distant world with seasons. It has become a potential home to alien intelligence, a neighbor that might be trying to communicate across the vast gulf of space. The stage is set for one of the most colorful and controversial chapters in the history of Mars exploration, a period when the line between science and imagination became beautifully, tantalizingly blurred. Mars was about to become not just an object of scientific study, but a mirror for humanity's deepest hopes and fears about our place in the universe. The Age of Canals and Dreams. As the 19th century draws to a close, Mars fever grips the world. In drawing rooms and lecture halls, in newspapers and scientific journals, people debate the possibility of Martian civilization with the same intensity they might discuss politics or religion. The Red Planet has become humanity's first serious candidate for harboring intelligent alien life, and the man most responsible for this transformation is a wealthy American businessman turned astronomer. Picture Lowell in 1894. A cultured Boston Brahmin who has made his fortune in the textile business, but whose true passion lies in the stars. At the age of 39, he makes a decision that will define the rest of his life. He will build an observatory dedicated solely to the study of Mars. He chooses a site in the clear, thin air of Flagstaff, Arizona, far from the light pollution and atmospheric turbulence of eastern cities. Imagine the scene as Lowell's observatory takes shape on Mars Hill, overlooking the frontier town of Flagstaff. Workers construct a dome to house a 24-inch refracting telescope, one of the finest instruments money can buy in 1894. The air at 7,000 feet elevation is crystalline clear, the kind of air that makes distant mountains seem close enough to touch and turns the night sky into a carpet of diamonds. But Lowell hasn't built this observatory to admire the general beauty of the cosmos. He has one specific target in mind: Mars and the mysterious canal network that Schiaparelli has reported. Lowell is convinced that these canals are the key to understanding not just Mars, but humanity's place in a universe that might be teeming with intelligent life. When Mars comes into opposition in 1894, Lowell begins his systematic study of the planet's surface. Night after night, he stands at his telescope, eye pressed to the eyepiece, carefully mapping what he sees. And what he sees astonishes him. Where Schiaparelli had detected dozens of canali, Lowell sees hundreds, a vast, interconnected network of straight lines crisscrossing the entire planet.
These aren't the meandering curves of natural riverbeds or the random cracks of geological processes. These lines are geometrically straight, purposefully engineered, clearly artificial. They form a global network that speaks of planning, of intelligence, of a civilization grappling with planetary-scale challenges. In the quiet hours after midnight, when the desert wind has died and Mars hangs steady in the eyepiece, Lowell constructs an entire narrative about Martian civilization. The planet, he theorizes, is dying. The polar ice caps that grow and shrink with the seasons represent Mars's last reserves of water, and the canal network is a desperate engineering project to transport this precious resource to the populated regions around the equator. The seasonal changes that Herschel and others had observed, the darkening and lightening of surface features, these aren't changing vegetation patterns, Lowell realizes. They're the result of cultivation. Martian farmers are irrigating their crops with water from the polar caps transported through the Great Canal system. When water arrives, the farmlands turn green and dark. When the water is diverted elsewhere, they fade to the lighter tones of fallow ground. Picture Lowell in his study, surrounded by his careful drawings of Mars, writing his observations in prose that reads like poetry. The aspect of the lines is perfectly distinct from that of natural waterways. They are not merely unlike, but the very reverse of what we see on Earth. Instead of running in a somewhat meandering course as rivers do, and broadening toward their mouths, as rivers also do, these Martian waterways are generally straight from source to termination and of uniform width throughout. Lowell publishes his findings in books and lectures that capture the public imagination like nothing since Darwin's theory of evolution. Mars and its canals, Mars as the abode of life. These aren't dry scientific treatises, but compelling narratives about a dying world and its desperate inhabitants. But Lowell's vision of Mars goes beyond mere scientific observation. In the Canal Builders of Mars, he sees a reflection of humanity's own future challenges. What happens when a world's resources begin to run out? How do intelligent beings respond to planetary crisis? The Martians, in Lowell's telling, have responded with unprecedented cooperation, putting aside whatever national, racial, or cultural differences they might have had to work together on projects of planetary scope. The canal network represents something beautiful and terrible. Beautiful in its testament to intelligence and cooperation, terrible in its evidence of desperation. Mars becomes a mirror for Earth's own future, a warning about the finite nature of planetary resources, and perhaps a hope that intelligence might find ways to overcome seemingly impossible challenges. Lowell's work has an impact far beyond astronomy. Writers and artists seize upon Lowell's vision of Mars as a dying world inhabited by an ancient, technologically advanced civilization. H.G. Wells, inspired partly by Lowell's observations, writes The War of the Worlds, imagining that the desperate Martians might turn their technological prowess toward invasion, seeking to escape their dying world by conquering Earth. Edgar Rice Burroughs creates John Carter, a Civil War veteran mysteriously transported to Mars, which he calls by its native name, Barsoom. Carter finds a world of red-skinned warriors and beautiful princesses, of ancient cities connected by the very canal network that Lowell has mapped from Earth. Ray Bradbury, decades later, will populate Mars with gentle, telepathic beings living in crystal cities, their civilization ancient and wise but fading like autumn leaves. The Mars of the Martian Chronicles is Lowell's Mars transmuted through the alchemy of imagination, a dying world whose inhabitants face their fate with dignity and grace. But even as Mars captures the popular imagination, other astronomers are having trouble seeing Lowell's canals. Using telescopes as good as or better than Lowell's, many observers report that Mars shows a mottled, patchy surface with no sign of the geometric network that Lowell maps with such confidence. What's happening? How can the same planet appear so different to different observers? The answer lies in the curious nature of human perception itself, and in the humbling realization that sometimes we see what we expect to see, especially when we're straining to make out details at the very limit of our instrument's capabilities. Modern analysis suggests that Lowell's canals were likely an optical illusion, the brain's attempt to connect discrete, barely visible surface features into continuous lines. The human eye and mind, evolved to detect patterns and make sense of incomplete information, were creating order from chaos, imposing geometric regularity on random surface markings.
But was Lowell wrong? In a purely observational sense, yes, there are no artificial canals on Mars. But in a deeper sense, Lowell was exploring something profoundly important: the possibility that intelligence might arise elsewhere in the universe, that we might not be alone in our cosmic home. His passionate conviction that life exists beyond Earth would inspire generations of scientists and explorers. Every Mars mission that followed, every rover that has rolled across Martian soil, every photograph that has revealed the planet's true nature, they all carry something of Lowell's wonder, his certainty that Mars had stories to tell and secrets to reveal. The whispers from Mars had grown into songs of possibility, and humanity was composing symphonies in response. The modern revelation.
As the 20th century unfolds, Mars begins to reveal its true face through the lens of increasingly sophisticated technology. The romantic vision of canal-building Martians gives way to a more complex but no less fascinating reality, a world that has indeed known flowing water, changing climates, and perhaps even life itself, though not in the forms that Percival Lowell had imagined. Picture the scene in 1965 at the Jet Propulsion Laboratory in Pasadena, California. Engineers and scientists gather around banks of primitive computers, their faces illuminated by the green glow of cathode ray monitors. They're waiting for humanity's first close-up glimpse of Mars, transmitted across 134 million miles of space by a tiny robot ambassador called Mariner 4. The images arrive as numbers, thousands of digital values representing different shades of gray, transmitted one painfully slow bit at a time across the vast gulf between worlds. As each line of data arrives, technicians convert the numbers into strips of paper, creating a mosaic that slowly reveals Mars as no human has ever seen it before. The first image shows a curved horizon against the black of space, proof that Mariner 4 has indeed reached its destination. But it's the subsequent images that deliver the shock. Instead of Lowell's network of canals connecting seas and continents, Mars appears as a cratered, moon-like desert. Ancient impact basins scar its surface like cosmic battlefields, speaking of eons of bombardment by asteroids and comets. In that moment, as the true face of Mars emerges from streams of digital data, humanity experiences both disappointment and wonder. The Mars of imagination, the world of dying civilizations and geometric canals, dissolves like a mirage. But in its place appears something equally remarkable: a real world with a real history, a planet that has endured and changed and evolved over billions of years. The craters tell stories of Mars's violent youth, when the solar system was still cluttered with the debris of planetary formation. Some are ancient beyond imagining, their rims softened by eons of dust storms and temperature changes. Others appear sharp and fresh, cosmically speaking, evidence that Mars continues to be shaped by celestial impacts, even today. As more Mariner missions follow, Mars begins to reveal its complexity. Mariner 9, arriving in 1971, finds the planet shrouded in a global dust storm, a phenomenon that makes the entire world disappear behind curtains of wind-blown particles finer than talcum powder. For weeks, the spacecraft can see nothing but the swirling, featureless cloud deck. But as the storm subsides, Mars emerges like a world reborn. And what a world it is! Mariner 9's cameras reveal features that dwarf anything on Earth. A canyon system so vast it could stretch from New York to Los Angeles, and so deep that it could swallow the Grand Canyon without a trace. This is Valles Marineris, the Mariner Valley, a scar across Mars that speaks of planetary forces beyond human comprehension. Even more dramatic is the discovery of Olympus Mons, a shield volcano so massive it defies earthly comparison. Standing 13 miles high, nearly 3 times the height of Mount Everest, and spanning an area larger than the state of Arizona, Olympus Mons is a monument to the geological forces that shaped early Mars. Its existence suggests that Mars was once far more geologically active than the cratered wasteland of the first Mariner images had suggested. But perhaps the most tantalizing discoveries are the features that suggest Mars once knew flowing water. Meandering channels snake across the planet's surface, carved by ancient floods that would have dwarfed any terrestrial deluge. Teardrop-shaped islands in these channels show the direction of long-vanished rivers. Delta-like formations mark where these waterways once emptied into seas and lakes that have been dry for billions of years. The seasonal polar caps that Earth-bound astronomers had observed for centuries proved to be made primarily of carbon dioxide, dry ice. The water ice lies beneath. But more intriguingly, Mars shows evidence of vast stores of water ice in its soil and in massive polar deposits that could, if melted, create oceans hundreds of feet deep.
This question drives the next phase of Mars exploration. If life had ever existed on Mars, where would we look for it? How would we recognize it? And could any Martian life have survived the planet's transition from a warm, wet world to the cold, dry desert it is today? The whispers from Mars have become more complex, more nuanced. The planet is not telling us about canal-building civilizations, but about something potentially more profound. The possibility that life is not unique to Earth, that biology might be a natural consequence of planetary evolution under the right conditions. Every new discovery raises new questions. The seasonal methane releases detected in Mars's atmosphere, could they be evidence of current biological processes? The recurring slope linea, dark streaks that appear on crater walls during warm seasons, could they be caused by briny water still flowing on Mars today? The discovery of organic compounds in Martian rocks, are they the fossils of ancient life or merely the result of non-biological chemistry? Mars has become our nearest laboratory for studying the fundamental questions of astrobiology. How does life begin? What conditions are necessary for its survival? Are we alone in the universe, or is life as natural and inevitable as gravity and starlight? Robotic ambassadors. The dawn of the 21st century brings a new chapter in humanity's relationship with Mars. No longer content to study the red planet from afar through telescopes, we begin sending robotic ambassadors to walk, or rather roll, across its ancient surface, to touch its rocks with mechanical hands, to taste its soil with electronic tongues. Picture the moment on July 4, 1997, when the Mars Pathfinder mission achieved something that would have seemed like pure science fiction to Percival Lowell just a century earlier. A small lander, cushioned by airbags, bounces across the Martian surface in a region called Ares Vallis before coming to rest in an ancient floodplain. As the airbags deflate and the lander's petals open like a mechanical flower, they reveal humanity's first Mars rover, a six-wheeled vehicle about the size of a microwave oven, equipped with cameras and scientific instruments. The rover is named Sojourner, after the American civil rights activist Sojourner Truth, and like her namesake, this little robot is breaking new ground in territory where none of her kind have traveled before. Sojourner's first images show a landscape that is both alien and strangely familiar. A rocky plain studded with boulders, all bathed in the butterscotch light of a sun that appears only half as large in the Martian sky as it does from Earth. But it's not just the alien landscape that captures our imagination, it's the profound intimacy of the experience. For the first time, we're not looking at Mars from millions of miles away through telescopes. We're there, in a sense, seeing the world through Sojourner's cameras, experiencing the daily rhythm of Martian weather, watching shadows wheel around rocks as the planet rotates on its axis. Sojourner spends 83 days exploring her small corner of Mars, analyzing rocks with whimsical names like Yogi, Barnacle Bill, and Scooby-Doo. Each rock tells a story. Some are volcanic basalts that speak of Mars's fiery youth. Others are conglomerates that formed in ancient rivers and lakes. The rover's tiny spectrometer reveals that Martian rocks contain many of the same minerals found on Earth, but in different proportions that hint at a different evolutionary history. As we watch Sojourner navigate around boulders and approach interesting targets, something magical happens. This mechanical explorer, with no more intelligence than a modern cell phone, becomes oddly endearing. We worry when she doesn't check in on schedule, celebrate when she successfully analyzes a new rock sample, and feel a strange pride as she exceeds her planned mission duration by more than 10 times.
Sojourner's success opens the floodgates for an era of Mars exploration more intensive and sophisticated than anyone had imagined possible. In 2004, twin rovers named Spirit and Opportunity land on opposite sides of Mars, carrying instrument suites more advanced than entire previous missions. These rovers, originally planned to operate for 90 Martian days, become the Energizer bunnies of space exploration. Picture Opportunity in 2004 landing in a small crater in Meridiani Planum with the kind of precision that would make a pool player jealous. The crater's exposed bedrock tells an immediate and fascinating story. These rocks formed in ancient shallow seas, their layers built up grain by grain over millions of years when Mars was a very different world. Opportunity's instruments detect the mineral signatures of ancient water everywhere. Hematite spherules, tiny iron-rich concretions that geologists call blueberries, litter the ground like ball bearings scattered by some cosmic child. These formed in standing water, precipitating out of mineral-rich solutions in ways that are impossible without sustained aqueous environments.
Meanwhile, on the other side of Mars, Spirit lands in Gusev Crater, chosen because it appears to be an ancient lake bed that received water from a large channel system called Maudim Vallis. But Spirit's initial findings are puzzling. Instead of the sedimentary rocks that would indicate a lake bottom, the rover finds volcanic basalts that speak of lava flows and impact processes. For months, Spirit trundles across these volcanic plains, her 6 wheels leaving the first tire tracks ever made by a human-built machine on another planet. The landscape is hauntingly beautiful. Rust-colored soil stretches to distant hills that rise like sleeping giants against a pale salmon sky. Dust devils dance across the plains, some towering hundreds of feet into the thin atmosphere, leaving dark swirls in their wake like brushstrokes on a cosmic canvas. Then Spirit makes a discovery that changes everything. After climbing to higher ground near the Columbia Hills, named after the crew of the space shuttle lost in 2003, the rover finds exactly what scientists had hoped to discover: clear evidence of ancient hot springs and hydrothermal activity. The rocks here tell stories of water interacting with minerals under pressure and heat, creating environments that, on Earth, are often rich with microbial life. Picture the moment when scientists realize what Spirit has found. In mission control rooms at NASA's Jet Propulsion Laboratory, researchers gather around computer screens showing microscopic images of Martian rocks. The structures they see, tiny formations in the rock that look like they could have been created by biological processes, send shivers of excitement through the room. Are these genuine biosignatures? The fossilized remains of ancient Martian microbes? Or are they merely the products of non-biological chemistry that happens to mimic the patterns of life? The question hangs in the air like incense, unanswered but tantalizing in its implications. Both rovers continue their missions far beyond anyone's wildest expectations. Spirit operates for more than 6 years before finally succumbing to the Martian winter, her solar panels covered with dust and her wheels stuck in soft soil. But Opportunity, remarkable, indefatigable Opportunity, continues rolling across the Martian landscape for nearly 15 years, covering more than 28 miles and returning over 200,000 images. Opportunity becomes more than a scientific instrument. She becomes humanity's first long-term resident of another world. Through her cameras, we experience Martian seasons, watching frost form on her solar panels during winter and dust storms engulf her in planet-wide tempests. We celebrate when dust devils clean her solar panels, extending her mission yet again,
And we worry during the months-long communication blackouts when major dust storms block out the sun. When Opportunity finally falls silent in 2018 after a global dust storm depletes her batteries one last time, the sense of loss is palpable. NASA's final transmission to the rover carries a poignancy that surprises everyone. "My battery is low and it's getting dark." These words, borrowed from a webcomic but adopted by the public as Opportunity's last message, capture something profound about our relationship with these mechanical explorers. They become extensions of ourselves, our eyes and hands on distant worlds, our ambassadors to the cosmos. When they succeed, we feel pride. When they struggle with technical problems, we feel concern. When they finally fall silent after years of faithful service, we mourn their loss as we would mourn the departure of faithful companions. The age of precision. As Opportunity and Spirit revolutionize our understanding of Mars's watery past, NASA prepares an even more ambitious mission. The Mars Science Laboratory, carrying a rover named Curiosity, represents a quantum leap in planetary exploration technology. Where previous rovers were the size of golf carts, Curiosity is as large as a small car. Where earlier missions carried a few simple instruments, Curiosity bristles with sophisticated analytical equipment that would be at home in any advanced Earth laboratory. Picture the scene on August 5, 2012, as Curiosity approaches Mars after a 9-month journey through interplanetary space. But this landing will be unlike anything attempted before. Instead of bouncing to the surface on airbags or using simple retro rockets, Curiosity will be lowered to the Martian surface by a sky crane, a mechanical angel that acts like a hovering platform, gently depositing its precious cargo before flying away to crash at a safe distance. The landing sequence, dubbed the 7 Minutes of Terror by NASA engineers, is a ballet of precision engineering performed at the speed of light across millions of miles of space. Radio signals take 14 minutes to travel between Earth and Mars, so the entire landing sequence must be automated, pre-programmed responses to a choreographed series of events that will either result in triumph or disaster. At Mission Control in Pasadena, hundreds of engineers and scientists hold their breath as telemetry signals from Curiosity indicate each successful stage of the landing sequence. Parachute deployment? Check. Heat shield separation? Check. Radar lock on the surface? Check. Spy crane separation and powered descent? Check.
Then, at 10:32 p.m. Pacific Time, the words that will echo through space exploration history crackle across the communication systems. Touchdown confirmed. We're safe on Mars. Curiosity has landed in Gale Crater, a 96-mile-wide impact basin that contains what may be the most remarkable geological formation on Mars, a mountain of layered sedimentary rock rising 18,000 feet from the crater floor. This mountain, officially named Aeolus Mons, but nicknamed Mount Sharp after geologist Robert P. Sharp, represents a 3 billion-year record of Martian environmental history written in stone. Each layer in Mount Sharp corresponds to a different epoch in Mars's past. Some formed in lake bottoms, others deposited by wind during more arid periods, still others created by volcanic ashfalls or impact debris. Reading these layers is like reading the pages of a cosmic library, each stratum telling part of the story of how Mars evolved from a potentially habitable world to the cold, dry desert we see today. Curiosity's first major discovery comes not from Mount Sharp itself, but from the ancient lakebed on Gale Crater's floor. As the rover analyzes rock samples with her sophisticated drill and laboratory instruments, she finds compelling evidence that this region once hosted a large freshwater lake. Not just for years or decades, but for millions of years.
The chemistry is perfect for life as we know it. The water was pH neutral, neither too acidic nor too basic. It contained dissolved minerals that terrestrial microbes use for energy. The environment was stable for geological time periods, providing the kind of long-term conditions that biological evolution requires. Picture the scientists analyzing these results, realizing that they're looking at evidence of the kind of environment where life began on Earth. For the first time, we have concrete proof that Mars once had habitable conditions, not just the presence of water, but the right kind of water with the right chemistry for the right duration. But Curiosity's most profound discovery may be her detection of organic compounds, carbon-based molecules that are the building blocks of life, in Martian rocks billions of years old. The compounds are simple ones, chlorobenzenes and thiophenes that could be produced by either biological or non-biological processes. But their mere presence in such ancient rocks suggests that Mars once had a carbon cycle, perhaps even a biosphere. Even more intriguing is Curiosity's detection of seasonal methane variations in the Martian atmosphere. Methane is a molecule that shouldn't persist long in the Martian environment. Ultraviolet radiation and chemical reactions should destroy it within a few centuries. The fact that methane concentrations rise and fall with the Martian seasons suggests an active source, something that's producing this gas in the present day. What could be producing methane on modern Mars? The possibilities are tantalizing. On Earth, over 90% of atmospheric methane is produced by biological processes: bacteria in swamps, termites in their mounds, the digestive systems of countless organisms. Could similar processes be occurring in Mars' subsurface, in hidden refugia where life might persist despite the planet's harsh surface conditions? Or perhaps the methane comes from geological processes, reactions between water and rock in Mars' interior, or the release of ancient gas deposits trapped in subsurface reservoirs. Either explanation would be significant, but the biological possibility carries implications that could revolutionize our understanding of life in the universe. As Curiosity continues her exploration of Gale Crater, slowly making her way toward Mount Sharp, she's joined by other robotic explorers. Orbiters circle overhead, mapping the planet in unprecedented detail and serving as communication relays for surface missions. The European Space Agency's ExoMars Trace Gas Orbiter analyzes atmospheric composition with sensitivity so high it could detect trace gases at concentrations of parts per trillion. Each mission builds on the discoveries of its predecessors, creating an increasingly detailed picture of Mars as a world that was once far more Earth-like than anyone had imagined. We now know that ancient Mars had thick atmosphere, flowing rivers, standing lakes, and possibly even oceans covering much of the northern hemisphere. The whispers from Mars have become a clear conversation, telling us stories about climate change on a planetary scale, of the gradual loss of atmosphere to space, of a world that might have hosted life for billions of years before conditions changed. These are not just stories about Mars. They're stories about planetary evolution, about the factors that make worlds habitable, about the fragility and resilience of planetary environments. The next generation. As we move deeper into the 21st century, Mars exploration enters an even more ambitious phase. The success of previous missions has proven that we can land sophisticated robots on Mars reliably, operate them for years beyond their planned lifetimes, and extract profound scientific insights from their discoveries. Now the focus shifts to questions that require even more advanced capabilities. Is there life on Mars today? Could Mars support human explorers? And ultimately, could Mars become humanity's second home? Picture the scene in February 2021 as 3 missions from 3 different space agencies arrive at Mars within a span of just 10 days. The United Arab Emirates Hope Orbiter slips into Martian orbit to study the planet's atmosphere and weather. China's Tianwen-1 mission deploys both an orbiter and a lander carrying the Zhurong rover. and NASA's Mars 2020 mission delivers the most sophisticated rover ever built to the red planet, Perseverance. Perseverance lands in Jezero Crater, another ancient lake bed, but this one is special. High-resolution images from orbiting spacecraft have revealed that Jezero once contained not just a lake, but a river delta, a fan-shaped deposit of sediments where an ancient river emptied into the standing water. On Earth, such environments are often rich in organic compounds and provide excellent conditions for the preservation of biosignatures.
But Perseverance carries capabilities that previous rovers could only dream of. She can drill rock samples and seal them in pristine containers for eventual return to Earth. She carries a small helicopter, the first powered aircraft to fly on another planet. And perhaps most remarkably, she can produce oxygen from the Martian atmosphere, demonstrating technology that future human explorers will need to survive. The helicopter, named Ingenuity, represents a triumph of engineering innovation. Flying on Mars is extraordinarily difficult. The atmosphere is less than 1% as dense as Earth's, equivalent to flying at an altitude of 100,000 feet above sea level. No helicopter has ever flown that high on Earth. To achieve lift in Mars's thin air, Ingenuity's rotors must spin at 2,800 revolutions per minute, nearly 10 times faster than a typical terrestrial helicopter. Picture that first flight on April 19, 2021, as Ingenuity lifts off from the floor of Jezero Crater. For 40 seconds, humanity has two active vehicles on the surface of Mars. Perseverance watching from nearby as Ingenuity hovers 10 feet above the ground before settling back to the surface. It's a Wright brothers moment for the space age, opening up entirely new possibilities for planetary exploration. But beyond the technological achievements, Perseverance's mission carries deeper significance. For the first time, we're not just studying Mars, we're preparing to bring pieces of Mars back to Earth. The rock samples that Perseverance collects will eventually be retrieved by future missions and returned to terrestrial laboratories, where they can be analyzed with instruments far more sophisticated than any rover could carry. This Mars sample return mission represents a new paradigm in planetary science. Instead of sending our instruments to Mars, we'll bring Mars to our instruments. Rocks that formed billions of years ago on another world will be studied in laboratories on Earth, searched for signs of ancient life with tools sensitive enough to detect individual organic molecules or fossil microbes. As Perseverance explores Jezero Crater, she's finding increasing evidence that Mars was once a world where life could have thrived. The delta deposits contain exactly the kinds of minerals and rock formations that preserve biosignatures on Earth. The chemistry of ancient lake sediments shows that conditions were suitable for a wide range of microorganisms. But perhaps most intriguingly, Perseverance has confirmed that organic compounds are common in Martian rocks. Not just the simple molecules that Curiosity found, but complex carbon-based compounds that could be the degraded remains of biological molecules. The concentrations are higher than scientists expected, suggesting that either Mars once had a rich carbon cycle or that life itself was contributing to the planet's organic inventory. The implications extend far beyond pure scientific curiosity. As we face climate change on Earth, Mars offers a cautionary tale about planetary atmosphere dynamics. The red planet shows us what can happen when a world loses its magnetic field and its atmosphere gradually bleeds away into space. But Mars also offers hope, evidence that even under harsh conditions, environments suitable for life can persist for geological timescales. Future Mars missions are already in development. NASA's Mars Sample Return campaign will use multiple robotic missions to collect Perseverance's samples and launch them toward Earth. The European Space Agency and Roscosmos are developing the ExoMars rover, equipped with a drill capable of reaching 2 meters below the surface, where organic compounds might be better preserved. And beyond the robots, human explorers are preparing for their own journey to Mars. NASA's Artemis program aims to establish a permanent human presence on the Moon as a stepping stone to Mars.
private companies like SpaceX are developing the heavy lift rockets and life support systems that could carry humans across interplanetary space. Picture that future day, perhaps in the 2030s, when the first human footsteps will leave their marks in Martian soil. Those explorers will stand in landscapes that robotic rovers have mapped in exquisite detail, but they'll see them with human eyes, experience them with human senses, and study them with the intuition and adaptability that only human intelligence can provide. The whispers from Mars continue, but they're no longer just scientific data transmitted across the void. They're becoming a conversation between worlds, a dialogue between humanity and the cosmos about the nature of life, the evolution of planets, and our own future as a spacefaring species. The search for life. Deep beneath the surface of Mars, in caverns carved by ancient water flow and chambers heated by the planet's slowly cooling interior, something extraordinary might be stirring. As we piece together the story of Mars exploration, we come to perhaps the most profound question of all. Are we alone in the universe, or does life persist on Mars even today? This question has evolved dramatically since the days of Percival Lowell's canals and Edgar Rice Burroughs' Green Warriors. We're no longer looking for technological civilizations or even complex organisms. Instead, we're searching for something far more subtle but equally revolutionary: microbes that might cling to existence in Mars's hidden refugia, extremophiles that could survive conditions that would instantly kill most terrestrial life.
Picture the deep subsurface of Mars, miles below the frozen, radiation-scoured surface that our rovers explore. Here, protected from the cosmic rays and ultraviolet light that sterilize the surface, conditions might be very different. Geothermal heat from Mars's interior could warm rocks and melt underground ice deposits. Chemical reactions between water and minerals could provide the energy that life needs to survive. On Earth, we've discovered thriving microbial communities in similar environments, in deep mine shafts, in boiling hot springs, in the crushing depths of ocean trenches. These extremophiles, as scientists call them, have adapted to conditions that early researchers thought were incompatible with life. They derive energy from chemical reactions rather than sunlight, build their bodies from carbon dioxide and methane rather than complex organic compounds, and reproduce in environments that would be instantly fatal to human beings. Could similar organisms exist on Mars? The evidence is tantalizing, but frustratingly ambiguous. The seasonal methane variations that Curiosity detected could be produced by methanogenic bacteria, similar to those found in Earth's swamps and deep ocean sediments. The organic compounds found in Martian rocks could be the degraded remains of biological molecules, broken down by radiation and oxidation over millions of years. Even more intriguingly, some Martian meteorites, rocks blasted off Mars by ancient impacts and eventually found on Earth, contain structures that look remarkably like fossilized bacteria. The most famous of these is ALH 84001, a potato-sized rock found in Antarctica in 1984. When scientists studied this meteorite in the 1990s, they found carbonate globules containing organic compounds, magnetic crystals, and tiny structures that some researchers interpreted as nanofossils, the mineralized remains of ancient Martian microbes. The announcement of possible life in ALH 84001 sent shockwaves around the world. President Bill Clinton called a press conference to discuss the implications. Scientists debated the findings with the intensity usually reserved for political controversies. The tiny structures in the meteorite became the most scrutinized microscopic features in history, examined and re-examined by researchers using every analytical technique available. The verdict, after decades of study, remains inconclusive. The structures could be fossils, but they could also be mineral formations created by non-biological processes. The organic compounds could be the remains of ancient life, but they might also represent contamination from Earth's environment or simple chemical reactions in space. This ambiguity is both frustrating and profound. It reminds us that the universe doesn't organize itself for our convenience, doesn't provide clear answers to our deepest questions. The search for life requires patience, humility, and the recognition that extraordinary claims require extraordinary evidence. But the search continues, driven by new discoveries that keep the possibility alive. In 2018, the European Space Agency's Mars Express orbiter detected what appears to be a large body of liquid water beneath Mars's south polar ice cap, a subglacial lake similar to those found beneath Antarctica's ice sheets on Earth. On our planet, such lakes teem with microbial life, organisms that have been isolated from the surface world for millions of years. Could Mars's subsurface lake harbor similar life? The water would be extremely salty, probably saturated with perchlorate salts that are toxic to most terrestrial organisms. But even on Earth, we found bacteria that thrive in hypersaline environments, organisms that use the salt-rich chemistry to their advantage. Perseverance's mission in Jezero Crater is specifically designed to search for biosignatures, chemical or physical evidence of past life. The rover's instruments can detect organic compounds at concentrations of parts per billion, identify mineral formations that are typically associated with biological processes, and even image potential microfossils at scales smaller than the width of a human hair. Every rock sample that Perseverance collects is a potential time capsule, preserving conditions from billions of years ago when Mars was warmer, wetter, and more hospitable to life. The sedimentary layers in Jezero Crater's ancient delta are like pages in a book, each one recording environmental conditions during a different epoch in Martian history. But perhaps the most profound aspect of the search for Martian life lies not in what we might find, but in what the search itself tells us about humanity. For the first time in our species' history, we have the technological capability to seriously investigate whether life exists beyond Earth. We're no longer limited to philosophical speculation or science fiction imagination. We can actually go to other worlds and look for life with our own instruments. This represents a watershed moment in human history, comparable to the development of agriculture, the invention of writing, or the discovery of DNA. Whether we find life on Mars or not, the fact that we can seriously search for it represents a fundamental expansion of human capability and knowledge. The whispers from Mars have become more complex, more nuanced. They speak not just of ancient rivers and vanished atmospheres, but of the deepest questions of biology and philosophy. They ask us to consider what life really is, how it begins, what conditions it requires to survive and evolve. If we do find life on Mars, whether fossilized in ancient rocks or persisting in hidden underground reservoirs, it will fundamentally change our understanding of biology and our place in the universe. We'll know that life is not unique to Earth, that the cosmos may be full of worlds where evolution has taken its own unique paths, created its own solutions to the challenges of existence. But even if we find that Mars is sterile, that would tell us something equally profound about the rarity and preciousness of life. It would remind us that Earth may be more special than we realized, that the conditions that allow life to flourish may be far more delicate and uncommon than we assumed. The human future. As our robotic ambassadors continue their patient exploration of Mars, humanity prepares for the next great leap, sending human explorers to walk on Martian soil. This isn't science fiction anymore. It's engineering reality, a challenge that's being tackled by space agencies around the world and private companies with names that would have sounded fantastical just decades ago. Picture a day in the not-too-distant future, perhaps sometime in the 2030s, when a sleek spacecraft carrying human beings will slip into orbit around Mars after a journey of 6 to 9 months through interplanetary space. The crew will have spent those months in a metal cocoon no larger than a small apartment, sustained by recycled air and water, watching Earth dwindle to a pale blue dot behind them, and Mars grow from a ruddy star to a world filling their viewports. The landing will be unlike anything attempted before. Where robotic landers have been small and expendable, a human Mars lander will be massive, a multi-story structure capable of keeping people alive in one of the most hostile environments imaginable. It will need life support systems, radiation shielding, communication equipment, scientific instruments, and enough supplies to sustain the crew until the next launch window opens for their return to Earth more than 2 years later. Imagine that first human to set foot on Mars, descending from the lander's airlock and stepping onto the rust-colored regolith. Through their helmet visor, they'll see a landscape that's been mapped in exquisite detail by decades of robotic exploration. But experiencing it with human eyes will be fundamentally different from watching it through rover cameras. The gravity will feel strange, about 38% of Earth's pull, light enough that each step will carry them farther than expected, but heavy enough to feel substantial. The sky will be a pale butterscotch during the day, deepening to blue around the sun and fading to pink at the horizon. The silence will be profound. No wind sounds through the thin atmosphere, no birds or insects, just the rhythm of their own breathing and the electronic hum of their life support systems. But this first human explorer won't be alone. They'll be part of a crew trained for years in geology, biology, engineering, and medicine. They'll have practiced their procedures in analog environments on Earth, in the Arctic, in deserts, in underwater habitats that simulate the isolation and confinement of a Mars mission. The challenges of a human Mars mission are staggering. The radiation environment of interplanetary space is far more hostile than anything humans have experienced in low Earth orbit. Cosmic rays and solar particle events can damage DNA and increase cancer risk. The psychological stress of being millions of miles from home, unable to communicate with Earth in real time, could push even the most mentally resilient individuals to their breaking points. But humans will bring capabilities to Mars that no robot can match. Where rovers move slowly and cautiously, analyzing single rocks over periods of days, human explorers can cover vast distances and make split-second decisions about which samples to collect. Where robotic instruments are limited to pre-programmed analyses, human intuition can spot unexpected features and adapt exploration strategies in real time. Picture human explorers working in the ancient river channels that rovers have mapped from orbit. They'll be able to follow sedimentary layers exposed in canyon walls, tracing the history of Martian water flow with their own eyes. They'll collect rock samples by the hundreds, not just the dozens that robotic missions can manage. Most importantly, they'll be able to drill deep into the Martian subsurface, searching for signs of current life in environments that surface missions can never reach. The scientific discoveries that human explorers could make on Mars might dwarf everything we've learned from robotic missions. But the human presence on Mars will represent something even more profound: the beginning of humanity's transformation into a multi-planetary species. The first human Mars missions will be exploration expeditions, lasting perhaps 18 months on the surface before the crew returns to Earth more than 2 years later. But subsequent missions will stay longer, establish more permanent facilities, and begin the process of creating a sustainable human presence on Mars.
This won't happen quickly or easily. A permanent Mars settlement will require massive infrastructure, habitats that can protect residents from radiation and dust storms, greenhouses where plants can grow in Martian soil, factories that can manufacture everything from spare parts to pharmaceuticals using local resources. Imagine a Mars settlement a century from now. The original landing sites have grown into small cities, their buildings constructed from Martian concrete and metals extracted from local ore deposits. Underground chambers carved from solid rock and pressurized with atmospheres thick enough to breathe house laboratories, workshops, and living spaces. The settlers, for that's what they'll be, will have adapted to life on a world with longer days, thinner air, and gravity that makes every movement feel light and flowing. Children born on Mars will know Earth only through stories and video transmissions, their bone density and muscle mass adapted to Martian conditions in ways that might make it difficult for them to ever visit their ancestral world. But perhaps the most profound change will be psychological and cultural. Humans living on Mars will develop new relationships with their environment, new ways of thinking about resources and sustainability, New forms of governance and social organization adapted to life in small, isolated communities where cooperation is literally a matter of survival. They'll also develop new relationships with Earth. The communication delay, ranging from 4 to 24 minutes depending on the planet's positions, will make real-time conversation impossible. Martian culture will begin to diverge from terrestrial culture, developing its own art, literature, philosophy, and science. The whispers from Mars will become conversations, then dialogues, then the complex cultural exchange between two branches of human civilization. Mars will teach us things we can't learn on Earth, about planetary geology, about the limits of life, about our own capacity for adaptation and survival. But more than that, Mars will give us perspective on Earth itself. From the vantage point of another world, we'll see our home planet as it truly is, a rare oasis of life in the cosmic desert, precious beyond measure, deserving of our protection and care. The red planet that has captured human imagination for millennia will become humanity's second home, a backup for our species and our culture, a laboratory for understanding how life and civilization can adapt to the challenges of different worlds. Terraforming dreams. As we peer further into the future, beyond the first human settlements on Mars, we encounter one of the most audacious ideas in the history of human thought: the transformation of Mars into a world where humans could walk outside without spacesuits, where liquid water could flow in rivers and lakes, where the sky might once again be blue and filled with clouds. This is terraforming, the deliberate modification of a planet's environment to make it suitable for Earth life. It's an idea that exists at the intersection of science and science fiction, of environmental engineering and planetary-scale ambition. Whether terraforming Mars is possible, practical, or even ethical are questions that scientists, engineers, and philosophers continue to debate. Picture Mars as it might exist thousands of years from now, after centuries of careful environmental modification. The atmosphere has been thickened through the release of greenhouse gases, warming the planet enough that the polar ice caps begin to sublimate, adding water vapor and carbon dioxide to the air. As the atmosphere thickens, it provides better protection from cosmic radiation and allows liquid water to exist on the surface. Plants, specially engineered varieties adapted to Martian conditions, begin to spread across the warming landscape. Their photosynthesis slowly adds oxygen to the atmosphere while removing carbon dioxide. Lichens and moss colonize the rocky surfaces, beginning the slow process of soil formation. In protected valleys, the first Martian forests take root, their leaves rustling in winds that carry the scent of growing things for the first time in billions of years. The methods for achieving such transformation are as varied as they are ambitious. Some scientists propose releasing super greenhouse gases into the Martian atmosphere, compounds thousands of times more effective than carbon dioxide at trapping heat. Others suggest installing giant mirrors in space to focus additional sunlight on Mars's polar regions, accelerating the sublimation of frozen carbon dioxide. More exotic proposals involve redirecting comets or asteroids to impact Mars, adding water and atmosphere through cosmic bombardment. Or perhaps engineering microorganisms specifically designed for Mars, bacteria that could thrive in the current Martian environment while producing the gases needed to transform it.
Carl Sagan captured this perspective perfectly when he wrote about the pale blue dot photograph taken by Voyager 1 from the outer reaches of the solar system. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of. Every human being who ever was lived out their lives. Mars amplifies this perspective. Every rover that has rolled across Martian soil, every orbital photograph of ancient riverbeds and polar ice caps, every analysis of Martian rocks and atmosphere reminds us that planets are dynamic, evolving systems.
They can change dramatically over geological time. Atmospheres can thicken or thin. Climates can shift from warm and wet to cold and dry. Life, if it exists, must adapt or perish. The story of Mars is ultimately a story about planetary stewardship. Mars appears to have lost its magnetic field early in its history, which allowed its atmosphere to be stripped away by solar wind. Without the protection of a thick atmosphere, surface water could no longer exist in liquid form. The planet that might once have been a blue world became the rusty desert we see today. Earth still has its magnetic field, still has its thick atmosphere, still has vast oceans that moderate temperature and weather. But we're learning that these protective systems are more fragile than we once thought. The greenhouse gases we're adding to Earth's atmosphere are changing our climate in ways that we're still trying to understand and predict. Mars offers us a laboratory for studying planetary atmospheric physics under conditions very different from Earth's. The seasonal behavior of Mars's carbon dioxide polar caps, the planet's dust storm cycles, the chemistry of its thin atmosphere, all of these phenomena help us understand the complex feedback loops that govern planetary climates. When we model Earth's future climate, we use some of the same physical principles we've learned from studying Mars. When we develop technologies for carbon dioxide removal or atmospheric engineering, we test our understanding against what we observe happening naturally on Mars. The red planet has become our classroom for planetary science. But perhaps Mars's greatest lesson concerns the nature of life itself. If we do find evidence of past or present life on Mars, whether in the form of ancient fossils, subsurface microorganisms, or complex organic chemistry, it will tell us that life is not a unique accident that happened once on one planet. Life may be a natural consequence of planetary evolution under the right conditions. This possibility fundamentally changes how we think about our place in the universe. Instead of being alone in an empty cosmos, we might be part of a vast community of living worlds, each developing its own unique biosphere, each contributing to the universe's complexity and beauty. Even if Mars proves to be sterile, it will still have taught us profound lessons about the conditions necessary for life to emerge and flourish. It will have shown us how precious and unlikely our own biosphere might be, how many factors must align perfectly for a planet to become and remain habitable over billions of years. The ancient astronomers who first noticed Mars's wandering motion across the night sky could never have imagined that their observations would lead to robotic explorers rolling across an alien landscape, to plans for human colonies on distant worlds, to dreams of transforming entire planets. But their patient observations, their careful record-keeping, their burning curiosity about the nature of the cosmos set in motion the chain of discoveries that bring us to this moment. Mars has also taught us about ourselves, about human ingenuity, persistence, and collaboration. Every successful Mars mission represents the combined efforts of thousands of people working together across decades. Engineers design and build spacecraft that must function perfectly after months in the harsh environment of interplanetary space. Scientists develop instruments that can detect trace amounts of organic compounds in rocks that formed billions of years ago. Mission controllers guide rovers across alien terrain using only photographs and computer models, making decisions that affect multi-million-dollar missions based on incomplete information received from millions of miles away. The exploration of Mars showcases humanity at its best: curious, collaborative, persistent,
and willing to invest enormous resources in the pursuit of knowledge and understanding. It reminds us that when we work together toward common goals, we can achieve things that would have seemed impossible to previous generations. Picture a child today looking up at Mars in the evening sky. That child might live to see human footprints in Martian soil, might witness the discovery of life on another world, might even travel to Mars as part of humanity's expansion across the solar system. The whispers from Mars that began with ancient astronomers thousands of years ago will continue to inspire new generations of explorers, scientists, and dreamers. But whether that child becomes an astronaut, a scientist, an engineer, or follows an entirely different path in life, they will grow up in a world where humanity is no longer confined to one planet. They will inherit a civilization that has learned to think in terms of multiple worlds, multiple environments, multiple possibilities for the future of life and consciousness in the universe.
But terraforming raises profound ethical questions that go beyond mere technical feasibility. If Mars harbors indigenous life, even simple microorganisms, do we have the right to transform their world to suit our needs? Would terraforming constitute an act of cosmic colonialism, the imposition of Earth-based life on environments that have their own evolutionary history? Some scientists propose paraterraforming instead, enclosing large areas of Mars under domes or other structures, creating Earth-like environments within protected spaces while leaving the rest of the planet unchanged. This approach would allow human settlement while preserving Mars's indigenous environment for scientific study. Imagine standing in a para-terraformed valley on Mars, perhaps 1,000 years from now. Through the transparent dome overhead, you can see the familiar salmon-colored Martian sky. But around you, the environment is transformed. Trees grow in soil enriched with Earth-imported organic matter. A stream flows past, fed by melted ice and recycled atmospheric moisture. Birds, descendants of Earth species adapted to Martian conditions, sing in the branches. Yet beyond the dome, the ancient Mars persists. The rust-colored plains stretch to distant mountains, unchanged from the world that captivated ancient astronomers. In carefully preserved areas, scientists continue to study Mars's indigenous geology and search for signs of native life, learning about billion-year-old ecosystems that evolved independently from Earth's biosphere. The transformation of Mars, whether through full terraforming or more limited para-terraforming, would represent humanity's first deliberate act of planetary engineering. The knowledge gained from such an endeavor would have profound implications for Earth itself, particularly as we face the challenges of climate change and environmental degradation. Terraforming Mars would require us to understand atmospheric physics, biogeochemical cycles, and ecological systems at unprecedented levels of detail. The techniques developed for thickening Mars's atmosphere might help us manage Earth's climate. The closed-loop life support systems designed for Mars colonies could inspire more sustainable technologies on Earth. But perhaps the most important aspect of terraforming isn't technical, it's psychological and cultural. The idea of transforming an entire world requires us to think on geological timescales, to plan for futures measured in millennia rather than decades. It forces us to consider our responsibilities, not just to our own generation, but to countless generations of humans and other species yet to be born. The whispers from Mars have evolved into something unprecedented, a conversation about humanity's role as a planetary species, about our capacity to nurture life on cosmic scales, about our obligations to the universe and to the future of consciousness itself. Whether Mars will ever bloom with Earth-like forests or ring with the songs of Earth-born birds remains an open question, but the very fact that we can seriously contemplate such possibilities represents a fundamental expansion of human vision and ambition. We are no longer merely inhabitants of Earth, confined to one small world in the cosmic darkness. We are potential gardeners of planets, architects of biospheres,
shepherds of life itself across the void between worlds.
Mars has whispered to us across billions of miles and millions of years. It has told us stories of ancient rivers and vanished atmospheres, of the possibility of life beyond Earth, of the challenges and opportunities that await us as we become a spacefaring species. But perhaps most importantly, it has reminded us that we are part of something much larger than ourselves, participants in the universe's ongoing experiment with complexity, consciousness, and life itself. The eternal dance. Every 26 months, like clockwork governed by the precise mechanics of celestial motion, Mars and Earth perform their ancient dance of opposition. Mars approaches as close to Earth as its elliptical orbit allows, sometimes coming within 35 million miles, a distance that sounds vast but represents intimate proximity in cosmic terms. During these oppositions, Mars blazes bright in Earth's sky, a ruddy beacon that is called to humanity across millennia. Picture the 2003 opposition, when Mars came closer to Earth than it had in nearly 60,000 years. Around the world, people gathered at observatories and in their own backyards, pointing telescopes at the red planet, hanging like an orange jewel in the constellation Aquarius. For a few weeks, Mars appeared larger in Earth's sky than it had during recorded human history, a reminder of the cosmic choreography that governs the motion of worlds. On that August night in 2003, a child in suburban Chicago pressed her eye to her grandfather's telescope eyepiece and saw Mars as a tiny orange disk, its surface features just barely visible as darker and lighter patches. In that moment, she joined an unbroken chain of observers stretching back to Galileo, to Tycho Brahe, to the anonymous Babylonian astronomers who first tracked Mars's wandering path across the star fields. That child, now an adult, might be working today on one of the Mars missions we've explored in our story. The wonder she felt that night, the sense of connection to something vast and mysterious, might have shaped her career choices, her education, her life's work. This is how Mars continues to inspire, not through grand pronouncements, but through quiet moments of wonder that plant seeds in curious minds. Each opposition brings new discoveries, new perspectives, new questions. The 2020 opposition saw 3 nations launch spacecraft toward Mars, demonstrating how Mars exploration has become a global endeavor. The 2022 opposition provided optimal viewing conditions for amateur astronomers, who contributed valuable observations of dust storms and atmospheric phenomena. Future oppositions will witness the launch of sample return missions, human expeditions, and perhaps the first attempts at large-scale planetary engineering. But oppositions are just the most dramatic moments in an ongoing relationship between our two worlds. Even when Mars is on the far side of the Sun from Earth, at what astronomers call superior conjunction, the red planet continues its patient orbit, continues its seasonal cycles, continues to weather dust storms and polar ice sublimation cycles that have been repeating for millions of years. This constancy, this reliability of celestial mechanics provides a kind of cosmic comfort. In a universe that can seem chaotic and unpredictable, the motions of planets follow mathematical laws that we can calculate with extraordinary precision. We can predict exactly when Mars will be closest to Earth, not just for the next century, but for the next 10,000 years, the next 10,000 years. Ancient astronomers understood this reliability intuitively, even if they lacked our modern understanding of gravitational physics. They recognized that the wandering stars, the planets, followed patterns that could be predicted, recorded, and used to organize human activities. The calendar systems that govern our daily lives still reflect the influence of these ancient observations. Mars has woven itself into human culture in ways both obvious and subtle. When we speak of something being martial or warlike, we're invoking the ancient association between Mars and conflict. When science fiction writers imagine alien worlds, they often begin with Mars-like deserts and alien skies. When we dream of human expansion into space, Mars is invariably our first destination beyond the Moon. But Mars has also influenced human thought in less obvious ways. The planet's seasonal changes contributed to early ideas about biological rhythms and environmental cycles. Its retrograde motion helped ancient astronomers develop the geometric concepts that would eventually lead to our understanding of planetary orbits.
Its visibility to the naked eye made it a universal human experience, shared across cultures and continents. Consider how many people throughout history have looked up at Mars and wondered. Shepherds in ancient Mesopotamia, watching their flocks under star-filled skies. Native American astronomers, incorporating Mars into their seasonal calendars and ceremonial cycles. Medieval Islamic scholars preserving and extending Greek astronomy knowledge during Europe's Dark Ages. Renaissance scientists using Mars to unlock the secrets of planetary motion. Each of these observers added something to humanity's understanding of Mars, and by extension, our place in the cosmos. Their observations, calculations, and insights form an unbroken chain of discovery that connects the ancient world to our current age of robotic exploration and future human settlement. This chain of discovery continues today and will extend into the future. Children born in the next few years may live to see the first human settlements on Mars, the first confirmation of extraterrestrial life, the first tentative attempts at large-scale planetary engineering. But they will also inherit the same sense of wonder that has driven Mars exploration from its beginning. They will still look up at the red planet in Earth's sky and feel the call to explore, to discover, to push the boundaries of human knowledge and capability. The whispers from Mars that began with ancient stargazers will continue to inspire new generations of explorers and dreamers. Mars has taught us that the universe is both larger and more intimate than we once imagined. It's larger because Mars shows us that planets are common, that solar systems are complex, that the universe contains countless worlds with their own histories and possibilities. But it's also more intimate because Mars demonstrates that worlds can be studied, understood, and even visited by creatures evolved on entirely different planets. The study of Mars has revealed the universe to be a place where physical laws operate consistently, where conditions that support life might be widespread, where intelligence might develop the capability to study and travel between worlds. This is a universe that rewards curiosity, that reveals its secrets to patient observation and careful analysis, that seems almost designed for exploration and understanding.
As we conclude this chapter of our cosmic story, Mars continues its eternal orbit around the Sun, continues its seasonal cycles, continues to hold its secrets close while gradually revealing them to our increasingly sophisticated instruments and ambassadors. The red planet that captured the imagination of our ancestors continues to inspire us today and will continue to call to future generations of human explorers. The whispers from Mars have grown into a conversation, a dialogue between worlds, an exchange of knowledge and wonder that enriches both the questioner and the questioned. Mars has taught us about planetary evolution, atmospheric physics, the possibility of life beyond Earth, and the nature of our own human drive to explore and understand. But perhaps most importantly, Mars has taught us that we are not alone. Not because we have found alien civilizations, but because we have learned that the universe is full of worlds, full of possibilities, full of opportunities for life and consciousness to emerge, evolve, and eventually reach out across the void to touch other worlds with curiosity and wonder. The Martian Seasons. As we delve deeper into the intimate details of Mars, we discover a world that breathes with its own rhythm, that experiences seasons as distinct and dramatic as Earth's, but lasting twice as long and painted in hues of rust and amber that no terrestrial autumn has ever known. Picture Mars as it cycles through its 687 Earth-day year, tilted on its axis at nearly the same angle as our own planet. But where Earth's seasons last 3 months each, Martian seasons stretch for 6 or 7 months, creating a leisurely progression of climate changes that unfold like movements in a cosmic symphony. In the Martian spring, the polar ice caps begin their spectacular retreat. The northern polar cap, composed primarily of water ice buried beneath seasonal layers of frozen carbon dioxide, starts to emerge from its winter shroud. As the sun climbs higher in the Martian sky and temperatures rise above the sublimation point of dry ice, vast quantities of carbon dioxide gas rush into the thin atmosphere, creating winds and weather patterns that dwarf terrestrial storms. Imagine standing on the edge of the retreating polar cap during the season of awakening.
The landscape around you is a study in contrasts, brilliant white ice fields stretching to the horizon, interrupted by dark patches where the underlying rock shows through. The air shimmers with sublimating gases, creating an ethereal dance of vapor and mist that catches the pale Martian sunlight like scattered diamonds. The seasonal changes on Mars are far more dramatic than anything we experience on Earth. As the polar ice caps sublimate, they release not just water vapor and carbon dioxide, but dust and debris that have been trapped in the ice for perhaps thousands of years. This material is caught up in the atmospheric circulation, creating dust storms that can grow from local disturbances to planet-spanning tempests in a matter of days. The Great Dust Storm of 2018, which lasted for months and eventually ended the Opportunity rover's mission, began as a small disturbance in the southern hemisphere during late spring. But the thin Martian atmosphere allows dust particles to remain suspended for enormous periods, and what started as a regional weather event gradually spread until it engulfed the entire planet in a shroud of suspended particles finer than talcum powder. Picture Opportunity during those final months as the dust storm of 2018 gradually darkened the Martian sky. The solar panels, already aging after 14 years of faithful service, struggled to collect enough sunlight to keep their systems alive. Day by day, the available power dwindled as the storm intensified, until finally, the brave little rover sent her last transmission and fell silent in the Martian gloom. But even as one chapter of exploration ended, the seasonal cycles that caused the storm continued their ancient pattern. Eventually, the dust settled, the skies cleared, and Mars emerged from its temporary shroud to reveal landscapes scoured clean by the global tempest. New features had been carved by the wind, old landmarks had been buried or transformed, and the red planet had once again demonstrated the awesome power of its meteorological processes. The seasonal behavior of Mars reveals the planet to be far more dynamic than early observers ever imagined. The dark regions that change with the seasons, features that early astronomers mistook for vegetation, are actually areas where seasonal winds remove or deposit fine dust, revealing the darker bedrock beneath or covering it with lighter-colored particles. Modern orbiters watch these changes in real time, creating time-lapse movies of Martian seasons that compress months of change into minutes of viewing. We can see dust devils dancing across the plains like towering tornadoes, their paths marked by dark swirls that persist for days or weeks. We can watch the polar caps advance and retreat with the rhythm of the seasons, their boundaries sharp as knife edges, where ice meets bare rock.
The hidden waters. Beneath the rusty, seemingly lifeless surface of modern Mars lies one of the solar system's most intriguing secrets. Vast reserves of water ice that could, if melted, create oceans hundreds of feet deep across the entire planet. This hidden hydrosphere represents not just a scientific curiosity, but potentially the key to Mars's future habitability and humanity's expansion into the cosmos. Picture the moment in 2008 when NASA's Phoenix lander, operating in the Martian Arctic, scraped away a few inches of surface soil and revealed something that gleamed white in the pale Martian sunlight. The white material sublimed away over the course of several sols, Martian days, proving conclusively that it was water ice, not salt or some other mineral deposit. This discovery confirmed what scientists had long suspected, that Mars's polar regions contain vast deposits of nearly pure water ice, mixed with soil in proportions that vary from a few percent to almost solid ice in some locations. Ground-penetrating radar aboard orbiting spacecraft has since revealed that these ice deposits extend for hundreds of miles and reach depths of more than half a mile in some regions. But the polar ice deposits are just the beginning of Mars's hidden water story. Across the planet, in regions where surface temperatures never rise above freezing, the soil contains significant amounts of water ice. The Mars Odyssey orbiter's neutron spectrometer has mapped this subsurface ice across the entire planet, revealing that vast regions of Mars are essentially permafrost.
permanently frozen ground containing more water than many terrestrial aquifers. Imagine drilling into the Martian soil in these ice-rich regions. A few feet down, your drill bit would encounter not just frozen soil, but layers of nearly pure ice laid down over thousands or millions of years, like geological layer cake. This ice represents precipitation from ancient Martian climates, times when the planet's axial tilt was different and polar ice caps extended much farther toward the equator. The implications of this buried water are staggering. Future human explorers on Mars won't need to transport all their water from Earth. They'll be able to extract it from the soil beneath their feet. The technology to do this already exists. Heating Martian soil to just above the freezing point of water would release water vapor that could be collected, purified, and used for drinking, manufacturing rocket fuel, or growing crops in Martian greenhouses. But perhaps even more intriguing than the ice in Mars's soil are the seasonal dark streaks called recurring slope lineae that appear on crater walls and hillsides during the warmest parts of the Martian year. These features, first discovered by the Mars Reconnaissance Orbiter, appear as dark lines that grow longer over time, suggesting the flow of some liquid down the slopes. Could liquid water still flow on modern Mars? The planet's low atmospheric pressure means that pure water would boil instantly at most locations, but water mixed with salts, brines similar to those found in Earth's most extreme environments, could remain liquid at much lower temperatures and pressures. The recurring slope lineae might represent seasonal seeps of briny water, emerging from underground sources during the warmest parts of the Martian year. The chemistry of these potential brines is fascinating and complex. Mars's soil contains high concentrations of perchlorates, salt compounds that are toxic to most Earth life, but which also dramatically lower the freezing point of water. A perchlorate brine could remain liquid at temperatures as low as -100 degrees Fahrenheit, well within the range of temperatures that Mars experiences during its warmer seasons. This possibility has profound implications for astrobiology. On Earth, we found microbial life thriving in hypersaline environments, in deep underground aquifers, and in other extreme conditions that would be lethal to complex organisms. If briny water does flow seasonally on modern Mars, these seeps could represent some of the most habitable environments on the contemporary red planet. Picture one of these recurring slope lineae during the Martian summer. The feature begins as a small dark spot near the top of a crater wall, perhaps where underground ice is melting due to seasonal warming or geothermal heat. Over the course of days or weeks, the dark streak grows longer, flowing downhill with the patience of geological time. The liquid, if it is liquid, moves slowly, perhaps only centimeters per day. But its passage leaves a dark stain on the Martian landscape that persists for months before fading as the water freezes or evaporates in the planet's thin atmosphere. From orbit, these features look like tears on the face of Mars, dark trails that speak of hidden moisture in an apparently arid world. The discovery of potentially flowing water on modern Mars has revolutionized our thinking about the planet's habitability. Instead of a completely dead world where life went extinct billions of years ago, Mars might harbor active habitable environments today. These environments would be extreme by Earth standards, high in salt content, low in temperature, exposed to radiation levels that would be lethal to most terrestrial organisms. But life, as we've learned from studying Earth's most extreme environments, is remarkably adaptable. Microorganisms have been found thriving in conditions that early biologists thought were absolutely incompatible with life. The discovery of potentially habitable brines on modern Mars suggests that the red planet might still host active ecosystems, hidden in its most protected and moisture-rich locations. The music of the spheres. In the vast silence of space, Mars sings. Not with sound waves that could travel through the vacuum between planets, but with electromagnetic frequencies that tell stories of solar winds interacting with thin atmospheres, of charged particles dancing in magnetic fields, of a world that resonates with cosmic energies in ways both subtle and profound. Picture the moment in 2021 when NASA's Perseverance rover deployed its microphones on the Martian surface, and for the first time in human history, recorded the actual sounds of another planet. The audio was haunting, a low, muffled recording of wind moving across the Martian landscape, filtered through an atmosphere so thin that sounds carry differently than they do on Earth. On Mars, sounds travel more slowly and are muffled by the thin atmosphere. High-frequency sounds are absorbed quickly, while lower frequencies can travel farther. If you could stand unprotected on Mars and speak to someone standing nearby, your voice would sound flat and distant, lacking the resonance that comes from sound waves bouncing off air molecules in Earth's thick atmosphere. But Perseverance's microphones captured more than just the whisper of Martian winds. They recorded the mechanical sounds of the rover itself. The whir of motors, the crunch of wheels on rocky ground, the zap of laser spectrometers analyzing rock samples. These recordings provided engineers with valuable diagnostic information about how the rover's mechanisms were performing in the Martian environment. But they also gave humanity something unprecedented, the soundscape of another world.
During Martian winter, the planet becomes a world of stark contrasts and bitter cold. Temperatures at the poles can drop to minus 195 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the atmosphere. The seasonal polar caps grow as atmospheric CO2 condenses directly from gas to solid, creating layers of dry ice that can be several feet thick. But even in winter, Mars displays a stark beauty that would take your breath away, if you could breathe on Mars at all. The thin atmosphere creates incredibly clear views of distant mountains in canyon systems. Without the haze and water vapor that softens terrestrial landscapes, Martian vistas have a crystal clarity that makes objects hundreds of miles away appear almost close enough to touch. The geology of time. To truly understand Mars, we must learn to think in geological time, to envision the red planet not as the static world we observe today, but as a dynamic, evolving planet whose surface tells the story of 4.5 billion years of cosmic history, written in stone, carved by water, and sculpted by wind. Picture Mars in its earliest days, shortly after the planet formed from the swirling disk of dust and rock that surrounded the young sun. The planet was a hellish world, constantly bombarded by asteroids and comets left over from the solar system's violent birth. Every impact released tremendous energy, melting rock and creating vast crater basins that would persist for billions of years. The largest of these ancient impacts created the Hellas Basin, a circular depression larger than Alaska and deeper than Mount Everest is tall. Standing on the rim of Hellas Basin today, you would look down into a bowl so vast that its far edge would be hidden by the curve of the planet itself. The impact that created this basin released more energy than every nuclear weapon on Earth detonated simultaneously, vaporizing rock and creating a temporary atmosphere of silicon and metal vapor. But the early bombardment period was just the beginning of Mars's geological story. As the planet cooled and the rain of cosmic debris diminished, more subtle but equally dramatic processes began to shape the Martian surface. Volcanic activity on a scale that dwarfs anything in Earth's history began to build the massive shield volcanoes that dominate the Martian landscape today. Olympus Mons, the largest volcano in the solar system, didn't form overnight. For hundreds of millions of years, eruption after eruption piled lava flows upon lava flows, building a mountain so massive that its base covers an area the size of Arizona
and its peak rises so high that it extends well above most of Mars's thin atmosphere. Imagine standing at the base of Olympus Mons, looking up at slopes so gradual you might not even realize you're standing next to a mountain. The volcano's flanks rise at angles of only a few degrees, so the ascent to the summit would be like walking up a very long, very gentle hill. But that hill would take you 13 miles into the sky, through atmospheric layers so thin that the summit exists in near vacuum conditions where water would boil instantly and unprotected humans would lose consciousness in seconds. The lava flows that built Olympus Mons tell stories of a Mars very different from the cold, dry world we see today. Each lava flow represents an eruption that lasted not days or weeks, but potentially centuries. Rivers of molten rock, some hundreds of miles long, poured down the volcano's flanks and spread across the surrounding plains, creating landscapes that look alien even by Martian standards. These volcanic plains, called the Tharsis region, represent one of the most geologically active areas on any planet in the solar system. The sheer mass of volcanic material piled up in Tharsis, estimated to be equivalent to moving all of Earth's continents into a single pile, actually warped the entire planet, creating a bulge that rises several miles above Mars's mean radius. But volcanism was not the only force shaping early Mars. As the planet's interior cooled and its magnetic field weakened, the thick atmosphere that had once protected the surface began to escape into space. Without magnetic protection, the solar wind stripped away atmospheric particles, gradually transforming Mars from a world that might have been warm and wet to the cold, dry desert we see today. This atmospheric loss left its signature in Martian rocks. Isotope ratios in the current Martian atmosphere show clear evidence of preferential loss. Lighter isotopes escape to space more easily than heavier ones, leaving the remaining atmosphere enriched in the heavier variants. It's like a cosmic distillation process that played out over billions of years, gradually concentrating certain elements while allowing others to escape forever into the void. During the period when Mars still had a substantial atmosphere, liquid water flowed across the planet's surface in quantities that boggle the imagination. The ancient river channels visible in satellite images aren't the remnants of small streams, but the scars left by floods that would have made Earth's greatest deluges look like gentle rain showers. The Casey Valleys system, carved by catastrophic floods billions of years ago, channeled water volumes estimated at hundreds times the flow of the Amazon River. These weren't brief floods. Geological evidence suggests they flowed for weeks or months, carving channels hundreds of miles long and tens of miles wide through solid bedrock. Picture those ancient Martian floods in your mind's eye. Imagine walls of water hundreds of feet tall racing across the landscape at speeds that would make modern automobiles seem sluggish. The roar of such floods would have been audible for hundreds of miles, a sound like continuous thunder that persisted for days or weeks as the deluge carved new channels through the ancient terrain. The teardrop-shaped islands left behind in these flood channels still dot the Martian landscape today, their pointed ends indicating the direction of flow like fossil compasses frozen in stone. These islands, some larger than Manhattan, were carved from solid bedrock by floods so powerful that they could move boulders the size of buildings as easily as a terrestrial stream moves pebbles.
The electromagnetic music of Mars is even more fascinating than its acoustic sounds. The planet's weak magnetic field, remnant of a time when Mars had a global magnetic dynamo like Earth's, creates complex interactions with the solar wind, the stream of charged particles constantly flowing outward from the Sun. Mars' atmosphere and volatile evolution, MAVEN, orbiter, has detected these electromagnetic phenomena in exquisite detail, recording the signatures of atmospheric escape, solar wind interactions, and the ghostly remains of Mars's ancient magnetic field. When converted to audio frequencies, these electromagnetic signals create an eerie soundtrack of whistles, clicks, and rising tones that sound almost like the songs of alien creatures.
These electromagnetic songs tell the story of Mars's atmospheric loss in real time. As solar wind particles strike Mars's upper atmosphere, they create electromagnetic waves that propagate through the planet's ionosphere like ripples on a cosmic pond. The frequency and intensity of these waves reveal how quickly Mars is still losing its atmosphere to space, a process that began billions of years ago and continues today. Each electromagnetic pulse represents atmospheric particles being stripped away and flung into interplanetary space, never to return. Over geological time, this process has transformed Mars from a world with a thick, protective atmosphere to the thin-aired planet we see today. The music of Mars is, in a sense, a requiem for a lost atmosphere, a cosmic song of environmental change played out over billions of years. But Mars also creates more familiar sounds that would be recognizable to any Earth dweller. Dust devils, towering columns of rotating air and suspended particles, create their own acoustic signatures as they move across the Martian landscape. These whirlwinds can tower hundreds of feet into the thin air, their cores generating low-frequency sounds that travel for miles across the planet's plains. Imagine listening to a Martian dust devil approaching across the landscape. The sound would begin as a distant whisper, gradually growing louder as the towering column of spinning air drew near. Unlike terrestrial tornadoes, Martian dust devils are relatively benign. Their low-density atmosphere means they lack the destructive power of Earth's twisters. But their acoustic signature would be unmistakable, a deep, thrumming sound that rises and falls as the vortex passes by. The study of Martian acoustics has revealed fascinating details about the planet's atmospheric properties. The speed of sound on Mars varies with temperature and atmospheric density, providing scientists with a new tool for understanding local weather conditions. Changes in wind speed and direction can be detected through variations in how sounds propagate across the Martian surface. More intriguingly, the acoustic properties of Mars might provide clues about subsurface structure. On Earth, seismologists use sound waves to probe the planet's interior, mapping underground geological features by analyzing how seismic waves travel through different types of rock and soil. Similar techniques could be used on Mars to search for underground water, cave systems, or other hidden features. The sounds of Mars represent more than just scientific curiosity. They provide an entirely new dimension of sensory experience for understanding alien worlds. For the first time, we can not just see Mars through cameras or analyze it through spectrometers, but actually hear what it sounds like to stand on its surface. This multi-sensory approach to planetary exploration enriches our understanding in ways that are difficult to quantify, but easy to feel. When we hear the wind blowing across Martian rocks or the mechanical sounds of rovers working on the planet's surface, we gain an intuitive understanding of Mars as a real place, not just an object of scientific study. The music of Mars continues to play, a cosmic symphony performed on electromagnetic instruments in frequencies both audible and invisible. Each sound tells part of the planet's story: its thin atmosphere, its dust-covered surface, its gradual loss of air to space, its complex interactions with solar radiation and charged particles. As we continue to explore Mars with increasingly sophisticated instruments, we'll undoubtedly discover new aspects of the planet's acoustic and electromagnetic environment. Future missions might deploy networks of seismometers and microphones across the Martian surface, creating a planetary monitoring system that listens to Mars with the attention they deserve. The colors of sunset. On Mars, the sunsets are blue. The simple fact captured by every rover and lander that has operated on the Martian surface encapsulates something profound about how alien worlds can challenge our earthbound assumptions about the nature of reality itself. Where Earth's sunsets paint the sky in reds and oranges, Mars offers a palette of blues and greens around the sun, with butterscotch and salmon hues dominating the rest of the sky.
This color reversal occurs because of the fine dust suspended in Mars's atmosphere. On Earth, our thick atmosphere scatters blue light strongly, making the sky appear blue during the day and allowing red and orange light to dominate at sunset, when sunlight must travel through more atmosphere. But Mars's atmosphere is full of iron oxide particles, rust dust, that scatter red and yellow light more effectively than blue light. During the day, this dust scattering gives Mars its characteristic butterscotch sky. But when the sun is low on the horizon and its light must travel through more atmosphere, something beautiful happens. The dust particles scatter away most of the red and yellow light, allowing the blue wavelengths to dominate near the sun itself. It's as if Mars and Earth have traded their sunset colors, each world expressing its unique atmospheric chemistry through the poetry of scattered light. The Martian day-night cycle creates its own rhythm of color changes that would become as familiar to future Mars colonists as earthly sunrises and sunsets are to us. The Martian sol, about 24 hours and 37 minutes long, is remarkably similar to Earth's day, making it easy for human circadian rhythms to adapt to Martian time. But the quality of Martian light is subtly different from terrestrial illumination. The sun appears smaller and dimmer, providing only about 43% as much light as it does on Earth. Colors appear muted, like viewing the world through sepia-tinted glasses. The famous red soil of Mars isn't actually as vibrantly red as it appears in many photographs. The planet's surface is more of a rusty brown, like the color of dried blood or autumn leaves. During Martian dust storms, the entire character of the sky changes dramatically. As fine particles fill the atmosphere, the sky takes on an ominous yellow or orange hue that can last for weeks or even months. The sun becomes a pale disk barely visible through the swirling dust, and the landscape takes on a twilight dimness even at midday. Imagine experiencing a global dust storm on Mars, a phenomenon that occurs roughly every 3 Martian years when conditions align perfectly. The storm begins subtly, perhaps as a slight haziness on the horizon that grows day by day. The normally clear views of distant mountains and crater rims gradually disappear behind curtains of suspended particles. The sky darkens from its normal butterscotch to deep orange, then to an apocalyptic brown that blocks most sunlight from reaching the surface. But even in the midst of these dramatic dust storms, Mars displays moments of extraordinary beauty. Lightning has been observed in Martian dust storms, electrical discharges created by friction between dust particles in the swirling atmosphere. These lightning bolts would create spectacular displays against the darkened sky, brief moments of brilliant illumination in a world temporarily shrouded in perpetual twilight. The dust particles that create these storms are incredibly fine, smaller than the particles in talcum powder. They can remain suspended in Mars's thin atmosphere for months, slowly settling out under the weak influence of Martian gravity. When the storms finally clear, they reveal a transformed landscape where familiar landmarks have been buried under layers of dust or scoured clean by the global winds. The colors of Mars tell stories that span geological ages. The planet's distinctive red coloration comes from iron oxide, rust, that formed when Mars had a more substantial atmosphere and liquid water on its surface. The iron in Martian rocks oxidized in the presence of water and oxygen, creating the iron oxide minerals that give Mars its characteristic hue. This rusty patina is actually a record of Mars's more habitable past. The oxidation of iron requires the presence of water, and in most cases, free oxygen. The fact that Martian rocks are thoroughly oxidized suggests that ancient Mars had not only liquid water on its surface, but possibly even oxygen in its atmosphere, conditions that could have supported complex chemical processes and potentially even life. The polar regions of Mars display their own unique color palette, especially during the dramatic seasonal changes when the carbon dioxide ice caps sublimate and reform. Time-lapse photography from orbiting spacecraft shows these regions as a constantly changing canvas of white ice, dark soil, and the complex patterns created by sublimating dry ice. During polar spring, the sublimation of carbon dioxide ice creates spectacular geysers that spray dark material hundreds of feet into the thin atmosphere. These geysers create fan-shaped patterns on the ice surface that look like abstract art painted on a cosmic scale. The contrast between brilliant white ice and the dark material ejected by the geysers creates some of the most visually striking landscapes in the solar system. Perhaps the most moving aspect of Martian colors is how they connect us emotionally to an alien world. The butterscotch sky and blue sunsets of Mars are beautiful in their own right, but they also serve as constant reminders that this is a world with its own character, its own atmospheric personality, its own way of interacting with sunlight and dust and the passage of time. Future Mars explorers will become intimately familiar with these colors, will learn to read the sky like a meteorologist reads weather patterns on Earth. They'll know that a certain shade of orange on the horizon means a dust storm is approaching. They'll appreciate the subtle beauty of a clear Martian morning when distant mountains stand out with crystal clarity against the pale sky. The eternal whisper. As our long journey through the story of Mars draws to its close, we find ourselves back where we began, gazing up at a red point of light in the evening sky. But now that light carries with it the weight of history, the excitement of discovery, and the promise of futures yet to be written. Tonight, somewhere in the world, a child is looking up at Mars for the first time, just as children have done for thousands of years. That child doesn't yet know about Mariner spacecraft or Viking landers, about spirit and opportunity and curiosity and perseverance. They don't know about ancient riverbeds or polar ice caps or the seasonal methane cycles that might hint at hidden life. All they know is wonder. They see a star that's different from the others, redder and somehow more mysterious. Perhaps their parent or grandparent tells them its name, Mars. Perhaps they learn that it's not a star at all, but another world, a place where robot explorers are rolling across alien landscapes at this very moment. In that child's wondering gaze, the entire story of human Mars exploration begins anew. The same curiosity that drove ancient Babylonian astronomers to track Mars's motion across the night sky, that inspired Kepler to unlock the secrets of planetary orbits, that motivated generations of scientists and engineers to send increasingly sophisticated machines across interplanetary space, now awakens in a new mind. The whispers from Mars that we've followed through this story, from ancient mythology to modern robotics to dreams of terraforming, continue. They speak to something fundamental in human nature, something that makes us look up at the sky and ask, what's out there? How does it work? Could we go there someday? These whispers have led us to discoveries we never could have imagined. We've learned that Mars was once a warmer, wetter world where life might have flourished. We've seen dust storms that engulf entire planets and ice caps that grow and shrink with seasons twice as long as Earth's. We've watched mechanical explorers navigate alien terrain with a grace and persistence that sometimes seems almost alive. But perhaps the most profound discovery is that Mars is not so different from Earth. Both planets formed from this same cosmic dust. Both were shaped by impacts and volcanism. Both knew flowing water and changing climates. Mars shows us what Earth might have become under slightly different circumstances, or what Earth might become if we're not careful stewards of our own planetary environment. This connection between worlds extends beyond geology and climate. Every successful Mars mission demonstrates humanity's capacity for long-term thinking, international cooperation, and the pursuit of knowledge for its own sake. The same qualities that Mars exploration requires, patience, persistence, curiosity, and the willingness to take calculated risks in pursuit of understanding, are the same qualities that will serve us well as we face the challenges of life on Earth. The story of Mars exploration is really the story of human potential. It shows us what we can accomplish when we combine scientific curiosity with engineering ingenuity, when we're willing to invest in projects that may take decades to complete,
when we value knowledge and discovery alongside more immediate concerns. As you drift off to sleep tonight, perhaps you'll dream of red landscapes under alien skies, of rovers making their way across ancient riverbeds, of future explorers taking their first steps on Martian soil. These dreams connect you to the long chain of dreamers and discoverers who have shaped our understanding of Mars and our place in the cosmos. The red planet continues its ancient dance around the sun, sometimes approaching Earth, sometimes receding into the cosmic distance, but always there, always visible to those who take the time to look up and wonder. Its whispers cross the void between worlds, carrying messages about the nature of planets and the possibility of life, about the rewards of curiosity and the power of human imagination. Mars waits for us, patient as stone, constant as starlight, ready to reveal more of its secrets to future generations of explorers. The whispers continue, soft and eternal, calling us to keep looking up, keep wondering, keep reaching across the darkness between worlds with the light of human curiosity and courage.
The Martian winds. The winds of Mars tell stories that span millions of years, carrying with them the memory of ancient climates, the promise of seasonal change, and the power to reshape entire landscapes with patience that makes human lifespans seem like heartbeats. These are not the gentle breezes of Earth's temperate zones, but alien currents that flow through an atmosphere so thin that their touch would be barely perceptible to human skin, yet strong enough to lift dust particles into globe-spanning storms that can rage for months. Picture yourself standing on the Martian plains during what passes for a calm day on the red planet. The wind flows around you with a whisper so soft you might mistake it for the sound of your own breathing echoing inside a spacesuit helmet. But this gentleness is deceptive. The same winds that feel like gentle caresses in Mars's thin atmosphere are moving at speeds that would constitute a hurricane on Earth. It's like being touched by the ghost of weather, wind that you can see but barely feel. Yet these ethereal currents have carved some of the most spectacular landscapes in the solar system. The Great Valleys Mariner's Canyon system shows clear evidence of wind erosion, where billions of years of atmospheric circulation have carved and sculpted rock formations into shapes that seem almost architectural in their precision. Wind has been Mars's primary landscape artist for the past several billion years, working with the patience of geological time to create beauty on a planetary scale. The seasonal wind patterns of Mars follow rhythms that would become as familiar to future colonists as Earth's weather patterns are to us. As the planet's polar ice caps advance and retreat with the changing seasons, they create pressure gradients that drive atmospheric circulation on a global scale. The sublimation of the southern polar cap during spring creates massive atmospheric disturbances that can trigger the planet-wide dust storms that occur roughly every 3 Martian years. Imagine experiencing the approach of one of these global tempests. It begins subtly. Perhaps orbital weather satellites detect the first stirrings of atmospheric disturbance near the retreating polar cap. Within days, local dust devils begin forming in unusual numbers, their dark tracks crisscrossing the landscape like the brushstrokes of an abstract painter. The horizon takes on a slight haze that grows more pronounced with each passing sol. Then, as if some cosmic switch has been thrown, the storm explodes into life. What began as scattered local disturbances suddenly coalesce into a massive weather system that can engulf entire continents within hours. The sky darkens from its normal butterscotch hue to deep orange, then to an apocalyptic brown as billions of tons of dust are lifted into the atmosphere. During the height of these storms, Mars becomes a world transformed. The familiar landscape disappears behind curtains of swirling particles. Surface temperatures drop as sunlight is blocked by the suspended dust. Solar-powered equipment struggles to function in the perpetual twilight. The planet becomes wrapped in its own atmospheric cocoon,
isolated from the sun's warming rays by a shroud of its own making. But within these chaotic storms, Mars displays moments of unexpected beauty. The dust-laden atmosphere creates optical phenomena that would take your breath away, if you could breathe on Mars. Dust devils become towering columns of golden light, illuminated from within by scattered sunlight. The sun, when visible at all, appears as a pale disk surrounded by concentric halos of light scattered by the suspended particles. Lightning flickers through the storm clouds, not the brilliant bolts we know from Earth's thunderstorms, but ghostly discharges created by the friction of countless dust particles rubbing against each other in the swirling atmosphere. These electrical displays create brief moments of illumination in an otherwise darkened world, revealing the vast scale of the atmospheric disturbance for just an instant before darkness returns. Modern Mars orbiters have revealed that these dust storms follow patterns that are both predictable and chaotic. The global storms tend to occur during southern hemisphere spring and summer, when Mars is closest to the Sun in its elliptical orbit, and the polar caps are sublimating most rapidly. But the exact timing and intensity of the storms depend on complex interactions between atmospheric temperature, pressure gradients, surface topology, and even the amount of dust available to be lifted from the surface.
Some regions of Mars are particularly prone to generating dust storms, areas where surface features create natural wind corridors that accelerate atmospheric flow. The Hellas Basin, that enormous impact crater larger than Alaska, acts like a giant atmospheric mixing bowl, creating circulation patterns that can spawn storm systems visible from Earth-based telescopes. The dust that these storms lift and redistribute has been traveling around Mars for millions of years. Particles that originated in ancient volcanic eruptions or impact events continue to circulate in the planet's atmosphere, occasionally settling out in new locations before being picked up by the next storm system. The fine reddish dust that coats everything on Mars is like a planetary memory bank, carrying chemical signatures from across the planet's surface and throughout its geological history. Future Mars explorers will need to develop an intimate understanding of these wind patterns, not just for practical reasons of equipment protection and mission planning, but because the winds of Mars carry information about the planet's past and present that can't be obtained any other way. The isotopic composition of atmospheric gases, the distribution of trace elements and dust particles, the seasonal patterns of atmospheric circulation, all of these provide clues about Mars's evolution and current state. Chapter 20. The Moons of Mars. High above the rust-colored plains of Mars, two tiny moons trace their ancient paths across alien skies, silent witnesses to the red planet's 4 billion-year history. These are not the large, round satellite we know from Earth's night sky, but small, potato-shaped chunks of rock that tumble end over end as they orbit, casting irregular shadows that dance across the Martian landscape in patterns that would seem magical to any Earth-born observer. Phobos and Deimos, named for the Greek gods of fear and panic who accompanied Ares into battle, are among the smallest moons in the solar system. Phobos, the larger of the two, is only about 14 miles across at its widest point, while Deimos is even smaller, barely 8 miles in diameter. If you could stand on the surface of either moon, you could probably throw a baseball hard enough to escape their weak gravitational pull entirely. Picture the view from Mars's surface as Phobos rises over the horizon. Instead of the stately, majestic ascent of Earth's full moon, Phobos races across the Martian sky like a cosmic speedboat, completing a full orbit in just 7.6 hours. It rises in the west and sets in the east, moving so quickly that you can actually see it change position against the background stars over the course of a few hours. During its rapid passage across the sky, Phobos appears as an irregular, lumpy shape that changes as the moon tumbles in its orbit. Sometimes it presents its longest dimension to viewers on Mars, appearing as an elongated oval. Other times it shows its narrow profile, looking like a cosmic football spinning end over end through space.
The surface features, craters and grooves carved by billions of years of impacts, create a constantly shifting pattern of light and shadow as the moon rotates. The origin of Mars's moons remains one of the great mysteries of planetary science. Unlike Earth's moon, which almost certainly formed from debris created when a Mars-sized object collided with early Earth, Phobos and Deimos don't fit neatly into any single formation theory. They could be captured asteroids, gravitationally snared from the nearby asteroid belt by Mars's gravity. Or they might be remnants of a larger moon that was shattered by a massive impact, leaving behind these two small fragments orbiting in its wake. The composition of the moons provide tantalizing clues about their origin. Spectroscopic observations suggest they're made of carbon-rich material, similar to certain types of asteroids, supporting the captured asteroid hypothesis. But their orbits are surprisingly circular and aligned with Mars's equatorial plane, exactly what you'd expect if they formed in place rather than being captured from elsewhere in the solar system. Phobos carries within its irregular bulk a cosmic time bomb that makes it one of the most doomed objects in the solar system. The Moon orbits so close to Mars, less than 4,000 miles above the planet's surface, that tidal forces are gradually pulling it apart. Every century, Phobos spirals about 6 feet closer to Mars, drawn inexorably toward its parent planet by gravitational forces that will eventually tear it to pieces. Imagine the spectacular end that awaits Phobos in the cosmic future, perhaps 50 million years from now. As the moon continues its inward spiral, it will eventually reach what astronomers call the Roche limit, the distance at which Mars's tidal forces become stronger than its own gravity. At that point, Phobos will begin to disintegrate, its rocky material spreading out along its orbital path to form a ring system around Mars. This future ring system would transform Mars from a planet with two small, irregular moons into a world adorned with rings that might rival those of Saturn in their beauty. Future Mars colonists, if humans still exist tens of millions of years from now, would look up at night to see delicate arcs of light stretching across their sky, the pulverized remains of ancient Phobos spread into a gossamer ring that catches and reflects sunlight in patterns of impossible beauty. But Phobos's doom is also Mars's gain in another sense. As the moon spirals inward, it transfers orbital energy to Mars's rotation, very slowly slowing the planet's spin. This process is so slow as to be almost imperceptible, but over billions of years it has helped stabilize Mars's rotation and may have contributed to the planet's current 24.6-hour day length.
Deimos, the outer moon, presents a very different character from its doomed sibling. Orbiting at a more respectable distance of about 14,000 miles from Mars, Deimos takes 30.3 hours to complete one orbit, longer than a Martian day. This means that from Mars's surface, Deimos appears to move very slowly across the sky, taking more than 2 sols to go from moonrise to moonset. Because of its small size and distant orbit, Deimos appears as little more than a very bright star from Mars's surface, certainly not the disk that Phobos presents. During its leisurely passage across the Martian sky, Deimos barely changes in brightness or appearance, moving like a cosmic clock hand that marks the passage of time in slow motion. Both moons are heavily cratered, their surfaces battered by billions of years of meteorite impacts. Phobos bears particularly intriguing surface features, long parallel grooves that stretch across much of the moon's surface like cosmic scratches. These grooves might be stress fractures caused by tidal forces from Mars, early signs of the gravitational forces that will eventually tear the moon apart. The largest crater on Phobos, named Stickney after the wife of the astronomer who discovered the moon, is so large relative to the moon's size that the impact that created it probably came close to shattering Phobos entirely. The crater is about 6 miles across on a moon that's only 14 miles wide, like a crater covering nearly half of Manhattan Island. For future Mars explorers, these tiny moons will serve as natural space stations and stepping stones for deeper space exploration. Their weak gravity makes them easy to land on and take off from, requiring minimal fuel expenditure. A spacecraft could easily hop from the surface of Mars to Phobos or Deimos, making them ideal locations for fuel depots, communication relays, or scientific observation posts. The moons could also serve as natural laboratories for studying the early history of the Mars system. If Phobos and Deimos are indeed captured asteroids, they might preserve chemical and isotopic signatures from the outer solar system, providing insights into the composition and evolution of the asteroid belt. If they're remnants of Mars's formation process, they could tell us about the planet's earliest history. From Mars's surface, the dance of its two small moons creates a sky that would be utterly alien to Earth-born eyes, yet hauntingly beautiful in its own way. Phobos racing from west to east, while Deimos crawls slowly in the opposite direction, their irregular shapes creating ever-changing patterns of light and shadow, their surfaces telling stories of cosmic violence and gravitational inevitability. The moons of Mars remind us that even in the apparent emptiness of space, every object has a story, every orbit tells a tale of gravitational forces and cosmic history. In their silent dance around the red planet, Phobos and Deimos carry with them the memory of Mars's past and the promise of spectacular transformations yet to come. The underground realm. Beneath the wind-swept plains and ancient crater fields of Mars lies a hidden world that may be more hospitable to life than the radiation-scoured surface above. This is the realm of underground Mars, a three-dimensional landscape of caves, lava tubes, underground rivers, and hidden ice deposits that could harbor ecosystems completely isolated from the hostile surface environment. Picture descending into one of Mars's lava tubes, those tunnel-like caves formed billions of years ago when molten rock flowed beneath the planet's surface. As you rappel down through the entrance, perhaps a collapsed section of tube roof that creates a skylight into the underworld, you leave behind the familiar rust-colored landscape of surface Mars and enter an alien realm where the rules of survival are completely different. The temperature in these underground chambers remains relatively constant year-round, insulated from the extreme temperature swings that characterize the Martian surface. While surface temperatures can range from 70 degrees Fahrenheit at the equator during summer to minus 195 degrees at the poles in winter, the underground maintains a steady temperature determined by Mars's internal heat and the insulating properties of solid rock. More importantly, these underground spaces are shielded from the cosmic radiation and solar ultraviolet light that sterilize the surface. On Earth, similar cave systems harbor complex ecosystems that thrive in complete darkness, deriving energy from chemical processes rather than photosynthesis. If life exists on modern Mars, these protected underground environments are among the most likely places to find it. Mars's lava tube systems are vast. Some individual tubes extend for hundreds of miles and could easily accommodate structures the size of city blocks. The Tharsis volcanic region, home to Olympus Mons and other massive shield volcanoes, contains lava tube networks that dwarf anything found on Earth. Some of these tubes are large enough that entire space stations could be built within their protective confines. Orbital imaging has identified thousands of potential cave entrances across Mars's surface, circular or oval holes that appear to be skylights into subsurface void spaces. Many of these entrances show no visible floor, even in the highest resolution images, suggesting cave systems that extend far deeper than our current instruments can detect. ground-penetrating radar from orbiting spacecraft has confirmed that many of these features do indeed connect to substantial underground voids. But perhaps most intriguingly, some of these underground spaces show signs of containing water ice or even liquid water. Temperature measurements from cave entrances suggest that some maintain conditions warm enough for liquid water to exist, at least seasonally. The combination of geothermal heating, protection from the surface temperature extremes, and possible access to groundwater makes these environments potentially habitable by Earth standards. Imagine exploring one of these systems with robotic probes designed specifically for underground exploration. The rover descends through a cave entrance using cables or perhaps small thrusters, its lights piercing darkness that hasn't seen illumination since the cave system formed billions of years ago. As it explores deeper into the system, it might discover underground chambers larger than football stadiums. Their floor is covered with ice deposits or even standing pools of briny water. The exploration of Mars's underground realm represents one of the next great frontiers in planetary science. While surface rovers have revealed much about Mars's geologic history and current environment, the subsurface remains largely unexplored. Future missions specifically designed for cave exploration could discover ecosystems that have been isolated from the surface world for millions or billions of years. These underground environments might preserve conditions from Mars's more habitable past. While the surface has been transformed by atmospheric loss and climate change, protected subsurface spaces might still harbor remnants of ancient Martian life forms that adapted to underground existence as surface conditions became increasingly hostile.
The geology of Mars's underground realm tells stories that are invisible from the surface. Lava tubes preserve records of ancient volcanic activity, their walls lined with mineral deposits that crystallized from hot gases millions of years ago. Impact-formed cave systems reveal the violence of Mars's bombardment period, when asteroid and comet impacts created underground shockwave patterns that fractured bedrock for miles around impact sites. Some underground spaces might contain mineral formations unlike anything on Earth. Crystals that grew over millions of years in the unique chemical environment of Mars's subsurface. Formations that could provide insights into the planet's geological and possibly biological history. These underground mineral gardens might be preserved museums of Martian chemistry, displaying the results of chemical processes that operated under conditions very different from those on Earth. For future human explorers, Mars's underground spaces offer natural shelter from radiation, temperature extremes, and dust storms. A Mars colony built within a large lava tube would require minimal construction of pressure-resistant habitats. The rock walls would provide natural pressure containment, radiation shielding, and thermal insulation. Underground colonies could be far more energy efficient than surface installations, requiring less heating and cooling to maintain comfortable living conditions. The underground realm also offers access to resources that might be difficult to obtain on the surface. Subsurface ice deposits could provide water for drinking, agriculture, and manufacturing rocket fuel. Underground mineral deposits might contain concentrated ores suitable for metal production. Cave systems could provide natural storage spaces for equipment, supplies, and even agricultural facilities. The study of Mars's underground environments has implications that extend far beyond the red planet itself. If we do discover life in Martian cave systems, it would prove that habitable environments can persist on planets even after surface conditions become hostile to life. This would dramatically expand our estimates of how many worlds in the universe might harbor life, including planets that appear sterile from space-based observations. Underground life on Mars would also provide insights into the limits of life itself, how organisms adapt to permanent darkness, extreme cold, high radiation, and isolation from surface ecosystems. These discoveries could inform our search for life on other worlds, particularly icy moons like Europa and Enceladus, where subsurface oceans might harbor ecosystems completely cut off from sunlight. The underground realm of Mars remains one of the planet's greatest mysteries, a hidden dimension that could completely transform our understanding of Martian habitability and the possibility of life beyond Earth. As we develop the technology to explore these underground spaces, we may discover that Mars is not a dead world at all, but a planet where life persists in hidden refugia, waiting to be found by explorers brave enough to venture into the darkness beneath the surface.